Hello there and welcome to Science for Sleep, where curiosity gets comfortable, complicated ideas are allowed to take their time, and the universe can be explored without anyone expecting you to take notes. Tonight, we're going to look at something rather unusual about the most familiar star in our lives, the Sun. We normally think of the Sun as a solitary object, one star sitting in the middle of the solar system, surrounded by planets, moons, asteroids, comets, and at least one species that occasionally complains when it becomes too warm. It seems completely natural to imagine that the Sun has always been alone. But it may not have been. There is a serious scientific hypothesis that, very early in its life, the Sun could have had a companion star. Not another sun sitting somewhere near Neptune, thankfully. If that were the case, astronomy would have noticed by now, along with everyone who enjoys nighttime. The idea is that billions of years ago, when the solar system was still forming, the young Sun may have belonged to a wide binary system. Two stars, born in the same environment, gravitationally connected for a time, moving together through the crowded stellar nursery where they formed. Then something happened. Perhaps another star passed nearby. Perhaps the changing gravitational environment of the Sun's birth cluster slowly pulled the pair apart. Perhaps the companion was pushed onto an orbit that eventually carried it away. Whatever the mechanism, the two stars may have separated, leaving the Sun to continue through the Milky Way by itself. And if that sounds a little like discovering that someone you've known your entire life may have had a sibling nobody mentioned, that's roughly where we are. So before we begin, I'd like to ask you a question. Where are you listening from tonight? Maybe you're somewhere where the Sun disappeared below the horizon several hours ago. Maybe you're still catching the last light of evening through a window. Perhaps it's raining. Perhaps the sky is clear. Or perhaps you've wisely decided that checking the weather can wait until morning. And when you think about the Sun, do you picture it alone? Most of us probably do. We learned the basic arrangement of the solar system when we were very young. Sun in the middle. Mercury, Venus, Earth, Mars, and the rest arranged around it. Sometimes Pluto was included. Sometimes it wasn't. Pluto has had a complicated administrative history, but the picture usually begins with one star. Tonight we're going to ask whether that picture might be missing someone. If you find these slow journeys through science relaxing, interesting, or simply useful, when you're trying to let the day become a little quieter, you can give the video a like and subscribe to Science for Sleep. It helps other curious and possibly slightly tired people find their way here as well. For now though, there's nothing you need to do. You don't need to remember names, calculate orbital periods, or develop an opinion about stellar dynamics before you fall asleep. We're simply going to follow the evidence and see why some astronomers have considered the possibility that the Sun's earliest history involved another star. And the first thing to understand is that having a companion would not make the Sun particularly strange. Stars are often social objects. When we look across the Milky Way, we find stars arranged in pairs, triples, and even more complicated systems. Two stars can orbit a shared centre of mass for millions or billions of years. Some binary stars are extremely close together, completing their orbits in hours or days. Others are separated by enormous distances and take centuries or longer to make a single circuit. Our own Sun happens to be single today. That doesn't necessarily tell us what its situation was when it formed. A major survey of nearby solar-type stars found that a substantial fraction belonged to binary, or higher-order multiple systems. In that field star sample, about 44% were found in systems containing more than one star, while about 56% were single. The important point is not that every Sun-like star must have a companion. They clearly don't. It's that a companion is ordinary enough that asking whether the Sun once had one is not an outrageous place to begin. And the young Sun was not born in the quiet environment we see around it today. Go back roughly 4.6 billion years, and there was no Earth to stand on, no moon in the sky, no Jupiter with its enormous collection of satellites, and certainly no small human wondering why the Wi-Fi has stopped working. There was a collapsing region of gas and dust. Within a much larger star-forming environment, material gathered under gravity. the central concentration became hotter and denser until the object that would become the Sun began taking shape. Around it, leftover material formed a rotating disk. Within that disk, tiny grains collided and stuck together. Larger bodies gradually formed. Planetesimals appeared. Protoplanets grew. The basic ingredients of the solar system began arranging themselves through gravity, collisions, heating, cooling, migration, and a truly unreasonable number of rocks crashing into other rocks. But the Sun was probably not the only star forming in the area. Evidence from meteorites and models of the Sun's birth environment points toward formation in a larger star-forming region rather than complete isolation. Exactly what that environment looked like remains an active subject of research, but the early Sun almost certainly had stellar neighbours much closer than the nearest stars are to us today. That matters because young stars do not politely ignore one another. Gravity does not recognise personal space. In a stellar nursery, nearby stars can alter one another's trajectories, wide binary systems can be disturbed, objects can be exchanged, small bodies orbiting one star can be pulled away or captured by another. Over time, as the cluster expands and disperses, stars that were once close neighbours can end up moving independently through the galaxy. The Milky Way gradually mixes everything together. A star born near the Sun could now be hundreds or thousands of light years away, depending on exactly how the two moved after their birth environment dissolved. After billions of years of orbiting the centre of the galaxy, interactions with the galactic disk, spiral structure, molecular clouds, and other gravitational influences can make reconstructing those early relationships extremely difficult. Imagine trying to find someone you briefly attended nursery school with, after both of you spent the next 4.5 billion years walking around a crowded city. The address book is not especially helpful. This is one reason the idea of a lost solar companion is so intriguing. If the Sun really did begin life in a binary, the other star would not necessarily need to have suffered some dramatic fate. It wouldn't need to explode or vanish into a black hole. It might simply have left. One model, published in 2020, examined what could happen if the early Sun had a companion of roughly comparable mass, orbiting at a very wide separation of around 1,000 astronomical units, while the Sun was still inside its birth cluster. An astronomical unit is the average distance between Earth and the Sun, so we're talking about a companion vastly farther away than any of the familiar planets. The proposal explored whether such a temporary binary could have affected the population of objects in the distant outer solar system. 1,000 astronomical units sounds enormous, and it is. Neptune orbits at about 30 astronomical units from the Sun. Pluto's average distance is roughly 40. So a companion star at around 1,000 astronomical units would have been far beyond the planetary region we recognise today. But in stellar terms, 1,000 astronomical units can still make a gravitationally connected pair. A wide one, certainly. The sort of relationship where both stars require plenty of space and probably communicate mostly by gravity. The important part is that a second star would have changed the gravitational reach of the young solar system. Today, the Sun dominates the motion of the planets, but things become less simple as we travel farther outward. Beyond Neptune lies a population of icy objects. Far beyond those lies an even more remote reservoir of bodies associated with the Oort Cloud, a huge and very distant population thought to surround the solar system. We haven't photographed the Oort Cloud as a neat shell sitting around the Sun. Its existence is inferred largely from the behaviour of long-period comets that arrive from extremely distant orbits. The outer solar system is so large that even our fastest spacecraft make our exploration efforts look rather modest. Voyager 1 has been travelling away from Earth since 1977. It has done remarkably well. But the distant solar system is the sort of place that makes nearly 50 years of spacecraft travel feel like popping down to the end of the driveway. The structure of those distant regions preserves information about what happened when the solar system was young. Planets migrate. Small objects scatter. Passing stars tug gently at distant bodies. The overall gravitational field of the Milky Way can influence extremely remote orbits. And if the young Sun once had a companion, that companion could have added another important source of gravity during a particularly sensitive period. This is where the hypothesis becomes more than a curious family story about the Sun. A second star might have left evidence, not a photograph. Nobody was taking those, not an ancient stellar name tag reading "property of the Sun's twin." Instead, the clues might survive in orbits. An object's orbit is partly a record of the gravitational events it has experienced. If you find a group of distant objects moving in unexpected ways, one possibility is that something influenced them. The difficult part is working out what. Perhaps a planet scattered them. Perhaps a passing star disturbed them. Perhaps the early cluster environment mattered. Perhaps there is an unseen distant planet. Or perhaps more than one of these things happened. The outer solar system is particularly useful for investigating the past, because many of its objects spend most of their time far from the massive planets. That doesn't mean their histories are simple, quite the opposite. It means small gravitational influences acting over enormous spans of time can become important. A companion sun could have increased the young system's ability to capture distant bodies or alter the formation of the Oort Cloud. The 2020 binary companion model, for example, proposed that a wide, roughly equal mass companion could increase the likelihood of producing the observed outer Oort Cloud population. The same study also explored whether a binary could have helped capture a distant planet, including the still hypothetical object usually called Planet 9. That last part needs a little care. Planet 9 has not been discovered. The name makes it sound rather settled, as though somebody has already assigned it parking and sent it a welcome package. They haven't. Planet 9 is a proposed distant planet that has been invoked to explain patterns seen in the orbits of some objects beyond Neptune. Whether such a planet actually exists remains unresolved. So when we talk about an early solar companion helping to capture Planet 9, we're stacking one interesting hypothesis on top of another. Science sometimes does this. Not because scientists enjoy making things unnecessarily complicated, although there are moments when the equations might suggest otherwise, but because hypotheses can be tested by asking what else they would predict. Suppose the Sun really did have a companion. What should the distant solar system look like? Would there be more captured objects? Would certain orbital patterns be easier to produce? Would the companion disrupt the planets too strongly, making the whole idea unlikely? Could it survive long enough to matter and then be removed naturally as the stellar cluster dispersed? Those are useful questions because they move the idea away from a story and towards something that can be examined quantitatively. And there is an important distinction here. The suggestion is not that astronomers have discovered evidence proving there was another sun. They haven't. There is currently no known star that we can point to and confidently say, there it is, that's the one. The lost companion idea is a model for part of the solar system's early history. It is interesting because binary and multiple star systems are common, because the Sun probably formed among other stars, and because the distant solar system contains structures whose origins are still being investigated. Whether those pieces belong to the same explanation is another question. That's what makes this such an enjoyable problem. We already know the ending, at least the present-day version of it. The Sun is alone now. There is no second star orbiting the Sun anywhere nearby. If there had once been a companion, the partnership ended a very long time ago, so we're working backward. Astronomers do this surprisingly often. You observe what exists today, then use physics to reconstruct what might have happened in the past. It's a little like entering a kitchen after someone has prepared dinner. There's flour on the counter, a warm pan on the stove, 3 mysterious spoons in the sink, and somehow a piece of onion has reached the windowsill. You didn't see the cooking, but you can make some fairly reasonable deductions. The solar system is our kitchen, although thankfully much larger and with fewer onions. Its planets tell us something about how material in the protoplanetary disk evolved. Meteorites preserve chemical information from the solar system's earliest period. Asteroids and comets preserve primitive material. The Kuiper Belt records a long history of migration and gravitational disturbance. The very distant objects beyond Neptune may preserve clues about influences that operated when the solar system was still embedded in its birth environment. And stars themselves carry information. Their ages, motions, and chemical compositions can be compared. Astronomers have already searched for solar siblings, meaning stars that may have formed in the same stellar group as the Sun. That is not quite the same thing as searching for a former binary companion. A birth cluster could have contained hundreds or thousands of stellar siblings, while a true companion would have been gravitationally bound to the Sun for some period. But the basic detective work overlaps: chemistry, age, motion, and attempts to reconstruct where stars have travelled through the Milky Way. Searches using large stellar surveys such as Gaia and Apogee have identified candidate solar siblings, but there is no secure identification of the Sun's original cluster family, much less a confirmed lost binary partner, which raises a rather strange possibility. If the companion existed and if it was not destroyed, that star could still be shining somewhere in the Milky Way right now. It might have planets. It might have spent the past several billion years following an entirely different orbit around the galaxy. And from the point of view of anyone living near that star, if anyone happened to be there, our Sun would be the missing one. Of course, finding such a star would be extraordinarily difficult. A star does not carry a visible record of every object it once orbited. Once a very wide binary is broken apart, the two components continue moving through the galaxy, and their trajectories are gradually altered by the environment around them. Rewinding billions of years of galactic motion is not as simple as playing a video backward. Small uncertainties grow. Stars encounter molecular clouds. Galactic structure changes. Gravitational perturbations accumulate. The farther backward you try to calculate, the less confident the reconstruction becomes. Chemical composition might help. Stars born from the same material can share detailed abundance patterns, rather like a broad chemical family resemblance. But stars can resemble one another chemically without having been binary partners, and identifying a genuine solar sibling after 4.6 billion years is already difficult. Identifying one particular sibling that may have once orbited the Sun would be a much tougher assignment, so we shouldn't get ahead of ourselves. Before we search the galaxy for a missing star, we need to answer something more basic. Could the Sun realistically have been born with one? If both stars were born together, how do two stars end up together in the first place? Stars look wonderfully self-contained once they reach adulthood. You see one bright point in the sky, and it feels like a complete object, neatly packaged by nature and delivered with its own gravity. Star formation is much less tidy. A star begins inside an enormous cloud of cold gas and dust. These molecular clouds can stretch across many light years and contain enough material to make hundreds, thousands, or even far more stars. They're not smooth clouds either. They contain denser pockets, thinner regions, filaments, knots, turbulence, magnetic fields, and material moving in different directions. Gravity works on all of it, slowly pulling the densest parts inward. Eventually, one region can become dense enough that gravity begins winning the argument. The gas collapses. As it falls inward, the central region becomes hotter and denser. A protostar begins forming at the centre, surrounded by material that has not yet fallen all the way in. Because the original cloud was rotating even slightly, that rotation becomes more important as the cloud contracts. The familiar example is a figure skater pulling in their arms and spinning faster. The collapsing gas behaves according to the same conservation of angular momentum, although with substantially more hydrogen and fewer sequins. Much of the remaining material settles into a rotating disk around the young star. That disk may eventually produce planets, but the collapsing cloud does not always decide to make only one star. Sometimes it fragments. Instead of all the material concentrating toward one central object, separate dense regions develop within the same collapsing structure. Each of those regions can continue contracting under its own gravity. If two of them become protostars and remain gravitationally connected, the result is a binary system. This is not a rare curiosity of star formation. Multiple star systems are a major part of the stellar population. A detailed survey of nearby solar-type stars found roughly 56% of the systems in its sample to be single, about 33% binary, and the remainder triples or systems containing still more stars. So while a lone sun is perfectly ordinary, having one or more stellar companions is also extremely common among stars broadly similar to our own. And when astronomers look at stars that are still extremely young, multiplicity becomes even more interesting. The Perseus molecular cloud offers one example. Astronomers use the Very Large Array to examine 94 protostars there, resolving companions over a huge range of separations. They found a substantial population of multiple systems, with the youngest Class 0 protostars showing especially high multiplicity. The distribution of companion distances also appeared to have two preferred scales, one around tens of astronomical units and another around thousands. That pattern suggests that more than one physical process can produce stellar companions. This is important for our missing companion. There isn't one single factory setting for making a binary. Two stars can emerge together because a larger collapsing core fragments into separate pieces. A disk around one young star can itself become unstable and produce another object. Protostars moving through a crowded environment can interact dynamically, changing partners, tightening or widening their orbits, and sometimes forming associations that did not exist at the earliest moment of collapse. Simulations of star-forming clouds find that both fragmentation and later dynamical interactions can contribute substantially to the population of multiple systems. So when we ask whether the Sun had a companion, we don't necessarily have to imagine a perfectly symmetrical birth in which one cloud split neatly down the middle and produced two identical yellow stars. Nature is under no obligation to arrange things that politely. The second star could have been somewhat smaller than the Sun. It could have been somewhat larger. It could have formed from the same collapsing structure at roughly the same time, or become associated with the young Sun through the complicated dynamics of the surrounding stellar nursery. The word twin can therefore be slightly misleading. It is useful because it gives us an immediate picture of two stars sharing an early history. But astronomers considering a former solar companion do not necessarily mean an identical twin in the everyday sense. They are talking about a stellar partner, possibly of comparable mass, gravitationally connected to the Sun during part of its youth. That distinction becomes especially important when we think about distance. When most of us picture a binary star system, we may imagine two suns circling close together, perhaps creating the sort of double sunset that has kept science fiction artists pleasantly employed for decades. Some binaries really are close. The stars can orbit one another at distances comparable to the scale of planetary systems. In extreme cases, they can be so close that they exchange material. Other binaries are much wider. Their stars may be hundreds or thousands of astronomical units apart. At those distances, the bond is far more delicate. Gravity still connects the two stars, but only weakly compared with a close binary. Passing stars and other disturbances can interfere much more easily. A wide binary is less like two people holding hands, and more like two people walking through a crowded railway station, while attached by an extremely long piece of string. It works until somebody walks through the middle. That vulnerability makes wide binaries especially relevant to the young Sun. The proposed solar companion we're considering would not need to have been sitting anywhere near the region where the planets were forming. One model explored a roughly equal mass companion at a separation on the order of 1,000 astronomical units. At that distance, the second star would have been far outside Neptune's present orbit and far beyond the main region of planet formation. If you could somehow stand on the young Earth, which you couldn't because the young Earth was going through a period in which standing anywhere was a fairly ambitious plan, that second star would not necessarily dominate the sky like another sun. Its apparent brightness would depend on its mass and distance, but it would have been vastly farther away than our own Sun. It might have appeared as an extraordinarily bright star rather than a second daylight-producing disk. More importantly, its gravity would still extend across the outer reaches of the young system. Wide companions are interesting precisely because stellar gravity operates over enormous distances. A star does not have a sharp gravitational boundary where its influence suddenly stops. The pull simply becomes weaker with distance and begins competing with the gravity of other objects. Near the Sun wins overwhelmingly. Move far enough away, and the gravitational environment becomes much more complicated. A companion at 1,000 astronomical units could therefore have mattered very little to a young planet close to the Sun, while mattering considerably more to objects hundreds or thousands of astronomical units away. That allows a binary hypothesis to avoid one immediate problem. We have a remarkably orderly set of major planets today. Their orbits are not perfectly circular or perfectly aligned, but the overall architecture tells us that the solar system was not repeatedly battered by a nearby second star passing directly through the planetary region. If the Sun once had a companion, it had to exist in a configuration compatible with the formation and survival of the planets. A sufficiently distant companion gives us some room. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune could remain primarily under the Sun's control, while the companion exerted more noticeable effects farther out. And young binary systems can contain planet-forming disks. The presence of another star does not automatically prevent planets from forming. The consequences depend heavily on the binary's separation, eccentricity, mass ratio, and how the disks are oriented. Even the survey of nearby solar-type stars found that planet-hosting stars occurred in both single and multiple systems, showing that stellar companionship and planet formation are certainly not mutually exclusive. We have discovered planets in several types of binary arrangements. Some orbit one member of a widely separated pair. Others orbit both stars in a close binary, following what astronomers call circumbinary orbits. Planet formation, apparently, is willing to work with whatever office space it is given. But our goal here isn't simply to show that binary stars exist, or that planets can survive around them. The more interesting question is whether the Sun itself belonged to one. Unfortunately, stars do not retain childhood photographs. We have to infer their origins from statistics, physics, chemistry, and whatever traces survive from the environments in which they formed. The statistics tell us that multiplicity is common. Observations of nearby solar-type stars show a large minority in binary or higher-order systems today. Observations of very young protostars show that companions can be particularly common during the earlier stages of stellar evolution. In Orion, for example, observations of hundreds of protostars again revealed numerous multiple systems and a separation distribution that differs from the mature solar-type stars we see in the galactic field. Some of the very wide young companions may later migrate inward, while others become unbound entirely. That last possibility is exactly the sort of thing we need. A star can begin life with companions and end life without them. Multiplicity is not necessarily permanent. Young stellar systems evolve dynamically. Orbits change. Triple systems can rearrange themselves. One member can be thrown outward, while the remaining pair becomes more tightly bound. Encounters with neighbouring stars can disrupt wide pairs. Gas disappearing from a young cluster changes its gravitational structure. The cluster itself expands, and stars that once occupied a dense environment begin spreading through the galaxy. In other words, looking at the solitary Sun today does not allow us to confidently conclude that it was solitary 4.6 billion years ago. The present is evidence. It is not the entire biography. This becomes easier to appreciate if we compress the Sun's life into something closer to a human scale. Imagine meeting someone at age 70 and learning that they now live alone. You wouldn't conclude that they had always lived alone. They might have grown up with brothers and sisters, shared a university flat with 5 people, and a refrigerator that nobody cleaned, married, moved several times, and eventually ended up in a quiet house by themselves. A star's environment changes too. The Sun today occupies a comparatively uncrowded region of the galaxy. The nearest star system, Alpha Centauri, is more than 4 light-years away. At that distance, its direct gravitational effect on the planets is negligible. The Sun's birthplace probably looked very different. Stars form inside molecular clouds, and many emerge as part of groups or clusters rather than in complete isolation. Young stars can initially be separated by much smaller distances than the distances between stars around the Sun today. Now place a very wide binary inside such a setting. The pair is already loosely connected. Around them are other young stars moving through the same environment. Some pass at distances that would be considered extremely close in astronomical terms. Every encounter slightly alters trajectories. Most encounters do very little. A sufficiently close or well-placed encounter can do quite a lot. The companion's orbit might become wider. Its direction might change. Eventually it might receive enough gravitational energy that it is no longer bound to the Sun at all. After that, the two stars simply separate. No explosion, no collision, no dramatic farewell detectable across the galaxy. One star follows one galactic orbit, the other follows another, and over billions of years the distance between them can become enormous. Modern simulations illustrate how fragile very wide binaries can be in dense stellar environments. Wide pairs experience strong disruption early in the evolution of clusters because encounters are more frequent when stellar densities are high. The exact survival rate depends on the cluster's density, structure, binary population, and other initial conditions, but the basic lesson is straightforward. A wide companion can be temporary. There is another twist. Some wide binaries may actually form while clusters are dissolving. As a young cluster expands, two stars leaving it with similar velocities and positions can sometimes become gravitationally bound, producing a very wide binary that did not begin as a primordial pair. N-body studies have shown that cluster dissolution can create binaries with separations of thousands of astronomical units or more. This gives us several possible routes. The Sun and its companion might have formed from the same collapsing material. They might have become a bound pair through early dynamical interactions. Their orbit might have changed substantially after formation, and eventually the pair might have been broken apart. You can already see why reconstructing this nearly 5 billion years later is difficult. Even if we somehow knew that the Sun had once been part of a binary, identifying the exact formation mechanism would be another problem entirely. But we can ask what kinds of binary configurations would have been physically reasonable. A companion extremely close to the Sun would strongly influence the protoplanetary disk. It could truncate the disk, excite eccentricities, alter where material remains stable, and leave obvious consequences for planet formation. Since our solar system extends comfortably through Neptune to 30 astronomical units, and contains additional populations much farther out, any proposed companion has to fit those constraints. Move the companion farther away, and its effects on the inner disk weaken. At several hundred or 1,000 astronomical units, you begin entering the range where a companion could leave the inner planetary region comparatively undisturbed, while still influencing much more distant material. That sounds convenient, and perhaps suspiciously so, but that's how scientific modelling often works. You start with what exists, then you ask what past conditions could have produced it, without destroying something else you know must survive. If your hypothetical companion sends Jupiter flying into interstellar space, the model has a problem. Jupiter is very much still here. If the companion strips away the entire protoplanetary disk before Earth can form, that's also inconvenient, particularly from our perspective. A viable model has to thread its way between these constraints, far enough away not to ruin the planets, close enough to matter in the outer solar system, bound long enough to influence distant objects, weakly bound enough that the crowded birth environment could eventually separate the pair. That is quite a specific job description for a star we aren't even sure existed. Yet none of those requirements is obviously impossible. Young stellar systems routinely undergo exactly these kinds of changes. Wide companions exist. Wide companions are disrupted. Multiple systems rearrange themselves. Stars escape clusters, clusters dissolve, the ingredients are real. The question is whether they were assembled in this particular way around our Sun. There is also no requirement that the companion survive for billions of years. In fact, if the hypothesis is going to explain why we see only one Sun today, it probably shouldn't. The interesting period would be early on, while the solar system's distant populations were still being assembled and while the Sun remained within or near its birth cluster. Once the companion had done whatever gravitational rearranging it was going to do, losing it could actually preserve the resulting structure. Think of stirring a cup of tea and then removing the spoon. The liquid continues carrying the motion you introduced even after the spoon is sitting beside the cup, making a small wet circle on the table. Orbits can preserve history in a similar way. Remove the object that caused a disturbance, and the altered trajectories do not automatically return to the way they were before. This is one reason astronomers are so interested in ancient orbital structures. They can act as fossils of gravitational events. The problem is that several different events can produce similar fossils. A passing star can disturb distant objects. A permanent companion can disturb them. A temporary companion can disturb them. Planetary migration can disturb them. The overall tidal influence of the Milky Way can disturb them. An undiscovered planet might disturb them. And because the solar system has been evolving for 4.6 billion years, these effects can overlap until the final pattern looks less like a clean fingerprint and more like a fingerprint left on a window after several people have tried to open it. This means we cannot work from multiplicity statistics alone. Saying that many stars have companions does not prove the Sun had one. It only establishes that the basic idea belongs within normal stellar behaviour. That's a useful first step. The Sun is not some special category of object for which binaries are forbidden. It formed through the same broad processes that make stars throughout the Milky Way. Those processes frequently produce pairs and larger multiple systems. Young systems evolve. Wide pairs can separate, so the hypothesis passes the first simple test. The Sun could have been born with company. Whether it actually was depends on the circumstances of its birth. The neighbourhood where the Sun was born was almost certainly nothing like the one it occupies today. Right now, our nearest neighbouring star system is Alpha Centauri, more than 4 light-years away. That is such an enormous distance that even light, moving fast enough to travel around Earth several times in a single second, takes more than 4 years to cross it. Space around us is not completely empty, but on the scale of stars, the modern solar system has plenty of room. The young Sun probably had considerably less privacy. Around 4.6 billion years ago, the material that produced our solar system was part of a much larger star-forming environment. Gas and dust were gathering into dense regions. New stars were appearing nearby. Some were small red dwarfs. Others may have been much more massive than the Sun. Many would have been surrounded by their own disks of material, each disk beginning its own experiment in making planets, moons, asteroids, and other objects from whatever happened to be available. Rather than imagining one baby sun sitting alone inside an enormous dark cloud, it is more realistic to picture an active stellar nursery containing many young stars at different stages of formation. Exactly how many stars shared the Sun's original environment remains uncertain. Different models produce different answers because they begin with different assumptions about radioactive enrichment, stellar encounters, disk evolution, and the structure of the young cluster. Some numerical studies have found that an environment containing a few thousand stars can reproduce several proposed constraints on the early solar system. One model, for example, favoured roughly 2,500 stars, while other workers placed the likely scale at 1,000 or more rather than a tiny isolated group. These are model-dependent estimates, not a recovered membership list from 4.6 billion years ago. Still, even the broad picture changes the way we should think about the Sun's childhood. Today, when another star passes within a few light-years of us, astronomers take notice. In the birth cluster, close stellar neighbours would have been normal. They would not necessarily have been close enough to produce a second bright disk in the daytime sky, assuming there had been an Earth with a daytime sky to begin with. Most of these stars could still have been separated by thousands or tens of thousands of astronomical units. But compared with the present distance to Alpha Centauri, that is a crowded room. And unlike people in a crowded room, stars affect one another without ever touching. Every star pulls gravitationally on every other star. Usually the effect is tiny. A distant star passes by, gives another system a slight gravitational nudge, and continues on its way. But young clusters offer millions of years for these encounters to accumulate. Some stars pass unusually close. Wide binary systems can be disturbed. Planet-forming disks can be trimmed. Small bodies can be scattered onto new orbits. In sufficiently close encounters, objects can even be transferred from one stellar system to another. This makes the Sun's birthplace important for understanding the solar system we see now. The planets did not form inside a sealed laboratory. The young Sun and its disk were exposed to whatever was happening around them. Researchers have used the present-day architecture of the solar system to constrain how disruptive that environment could have been. The planets have relatively orderly orbits, and parts of the Kuiper Belt preserve dynamically delicate populations that could not have survived unlimited harassment from passing stars. Studies of stellar encounters in birth cluster environments therefore place limits on combinations of stellar density and the amount of time the Sun could have spent. The neighbourhood could be busy, but apparently not so violent that every distant orbit was scrambled beyond recognition. It's the astronomical equivalent of knowing someone grew up in a large household, because there are family photographs everywhere, while also knowing that the household probably wasn't hosting indoor demolition competitions every weekend, because some of the furniture survived. Meteorites give us another kind of clue. Some of the oldest solid material in the solar system contains evidence that short-lived radioactive isotopes were present when the planets were beginning to form. These radioactive atoms have long since decayed, but their daughter products can remain behind, allowing scientists to reconstruct aspects of the chemical environment in which the earlier solar system material formed. The interpretation is complicated, and researchers do not agree on a single simple story in which one nearby supernova conveniently delivered every interesting isotope at exactly the right moment. Different radionuclides can have different origins, and some models involve enrichment of the Sun's parent molecular cloud before the solar system itself fully formed. Even so, these chemical records have been used to investigate whether massive stars existed in the broader environment associated with the Sun's formation. Models connecting the solar system's isotopic inventory with its birth setting often place the Sun in a substantial star-forming region rather than in complete isolation. That gives us a useful picture. There is the young Sun, still surrounded by a disk. Jupiter has not yet become the enormous planet we know today, or perhaps is somewhere in the process of doing so. The smaller rocky planets are not finished. Countless planetesimals occupy the disk. Collisions are common. Material moves inward and outward. Gas still plays an important role. Beyond the Sun's own system are other young stars. Some are close enough to matter gravitationally. One of them may be much closer than the others. This is where our possible companion returns. Imagine moving outward from the young Sun. You pass the region where Mercury will eventually orbit, then Earth's future neighbourhood, then the region of the giant planets. You continue past Neptune's present distance, around 30 astronomical units. Keep going. 100 astronomical units, 200, 500. At these distances, the Sun still holds objects gravitationally, but we are far beyond the familiar planetary system. Continue until you reach something like 1,000 astronomical units, 1,000 times the average distance between Earth and the Sun. In the model proposing an early solar binary companion, this is roughly the scale at which another star of comparable mass could have orbited the young Sun. It would have been an extremely wide binary. The exact configuration is hypothetical, but a companion at around 1,000 astronomical units is particularly interesting because it could influence very distant material while avoiding the much more severe disruption that a close stellar companion could cause within the planetary region. Try to picture those two young stars from far above the system. The Sun is not fixed at the centre, with the companion doing all the orbiting. That is not really how a two-body system works. Both objects orbit their common centre of mass. If the two stars had similar masses, that centre would lie roughly halfway between them. Each star would travel around it on a large orbit, taking many thousands of years to complete one circuit, depending on their exact masses, separation, and orbital shape. Around the Sun itself, meanwhile, the planetary disk continues developing. From close in, the Sun's gravity dominates. Farther away, the gravitational situation becomes more interesting. There are now two stellar masses helping to define which distant trajectories are stable, which objects can be captured, and which ones are easily lost. And surrounding the entire arrangement is the birth cluster. This is where calling the companion the Sun's twin becomes useful, as long as we remember what the word does and does not mean. We do not know that the companion existed. If it did exist, we do not know its exact mass. We certainly do not know that it looked identical to the Sun. It might have been somewhat smaller. It might have been somewhat larger. It may have had its own protoplanetary disk, and perhaps begun forming its own planets. The equal mass companion considered in one influential version of the hypothesis is a useful model because it allows researchers to calculate how a broad binary could affect the distant solar system. It is not a photograph of what actually happened. Still, an approximately solar mass companion gives us an interesting possibility. There may once have been two young stars moving together through the Sun's birth cluster. Both formed from the same general stellar nursery. Both would have been exposed to many of the same neighbouring stars. Both travelled through the same surrounding gas and radiation environment. For some period, their futures were connected by gravity, and neither would have had any idea that one of them was eventually going to become significantly more famous because a small rocky planet around it developed astronomy. If we could observe this system from somewhere outside it, we might not find the arrangement particularly extraordinary. Wide stellar pairs exist. Young multiple systems exist. Stellar nurseries produce complicated arrangements in which stars interact and systems evolve. The unusual part is only that one member of this possible pair happens to be ours. There is a temptation here to imagine that the companion would have been an obvious second sun hanging in Earth's sky, but Earth probably did not yet exist in anything resembling its modern form during the period that matters most to this hypothesis. Planet formation began while the Sun was still very young. Dust grains stuck together, larger solids accumulated, kilometre-scale bodies formed, embryonic planets collided and grew. The terrestrial planets required tens of millions of years to reach their final forms through repeated impacts and gravitational interactions. A wide binary companion could have disappeared from the scene before the solar system settled into the mature configuration we recognise. There may never have been an afternoon on modern Earth with two suns overhead, which is unfortunate for cinema perhaps, but considerably more convenient for orbital stability. The companion's real importance would have been much farther out. At large distances from the Sun, objects move slowly and are only weakly bound. A comparatively small gravitational disturbance can have a large effect on their final orbits. This is one reason the Sun's birth cluster itself has received so much attention. A passing star could approach the young solar system and change the orbit of a distant object without having any noticeable effect on Earth. Sedna provides a famous example of the problem. Sedna is a distant body whose orbit is unlike those of ordinary Kuiper Belt objects. It travels on a highly elongated path and never comes particularly close to Neptune. Its perihelion is around 76 astronomical units from the Sun, far enough away that Neptune cannot easily explain its current orbit through ordinary close scattering. One possible explanation is that Sedna's orbit records something that happened when the Sun was still near other stars. Long before anyone proposed a lost solar companion as an explanation for the distant Oort Cloud, researchers were already investigating whether a stellar encounter in the Sun's early environment could place objects onto Sedna-like orbits. Numerical work has shown that a passing star under suitable conditions can strongly modify bodies in the distant planetesimal disk and produce unusual eccentric orbits. In some encounter scenarios, material could even be captured from another star's own disk. That is worth thinking about for a moment. Some object orbiting the Sun today could, at least in principle, have started around another star. We do not currently have evidence that Sedna itself was stolen from a neighbour. The point is that early stellar encounters make this kind of exchange physically possible under certain conditions. The young solar system was not necessarily a closed family. Material could leave, material could arrive, and if the Sun had a binary companion, the possibilities increase. Two stars provide a larger gravitational target than one. Together they can interact with passing objects differently from a solitary star. In the temporary binary model, this increased gravitational capture efficiency is one reason the companion was proposed in the first place. A wide early binary could potentially help populate the distant Oort Cloud with more objects than an isolated young sun could capture under the same general birth cluster conditions. But before getting to what it might capture, notice the balancing act required just to keep the companion around. 1,000 astronomical units is a very wide separation. The two stars are bound, but not tightly. Now put them inside a cluster containing hundreds or thousands of other stars. A third star passes at some distance. Its gravity slightly changes the orbit of the pair. Later another passes, then another. The cluster itself evolves. Gas is expelled. Massive stars lose material through winds. Some explode as supernovae. Stars move outward. The overall gravitational potential changes as the original group expands. A wide binary living through all of this has a rather uncertain lease. It may survive, its orbit may change, or it may be broken apart. That last outcome is exactly what the lost companion hypothesis requires. The same environment that makes the pairing plausible also provides a natural way to end it. The Sun would not need to eject its partner through some mysterious internal process. The birth cluster could do the job. Imagine the Sun and its companion orbiting one another while another star approaches. Most approaches do almost nothing. Then eventually a particular encounter occurs with the right distance, speed and direction. The passing star tugs on the companion. Energy is exchanged between the three bodies. Perhaps the Sun and its companion emerge with a wider orbit. Perhaps the companion leaves with slightly more energy than before. Once its orbital energy becomes high enough, the gravitational connection is broken. The companion is no longer coming back. There is no boundary line for it to cross and no moment when a small light turns on saying, "Binary status cancelled." It simply moves onto an unbound trajectory. At first, the two stars might still remain relatively close by astronomical standards. A few thousand astronomical units, then tens of thousands. Then perhaps a fraction of a light year. Eventually light years. As the cluster disperses, the Sun and its former partner become two independent stars orbiting the Milky Way. Numerical studies of solar birth cluster evolution show how dramatically such groups can spread over galactic time. Simulations following the disruption of plausible solar birth clusters find that the Sun's original stellar siblings can become distributed widely through the galactic disk, with their present locations depending strongly on both the cluster's initial properties and the gravitational history of the Milky Way. And that creates one of the stranger consequences of the whole idea. The Sun's possible twin may not be gone, it may simply be somewhere else. If the star survived normally, then 4.6 billion years is not necessarily enough time to kill a Sun-like star. A star of approximately one solar mass can remain on the main sequence for roughly 10 billion years, depending on its exact mass and composition. A somewhat smaller companion could remain stable for far longer. In other words, if the companion existed, there is a perfectly reasonable scenario in which it is still shining today. not hidden beyond Pluto, not lurking behind the Sun, not secretly orbiting us beyond the Oort Cloud, somewhere in the Milky Way, perhaps hundreds of light years away, perhaps much farther. Its exact location would depend on how quickly it separated from the Sun and everything that happened to both stars afterward. That means there are really two different searches involved when astronomers discuss the Sun's original family. One search is for solar siblings, stars that formed in the same stellar nursery as the Sun. The other, much more specific search would be for a former gravitational companion. Every former companion would probably qualify as a solar sibling in a broad chemical and chronological sense if it formed from the same material, but almost every solar sibling would not have been the Sun's binary partner. If the birth cluster contained a few thousand stars, then our hypothetical companion would be one particular person in a very large family photograph. And the photograph is missing. Astronomers therefore try other methods. Stars formed from the same well-mixed material can have similar chemical abundance patterns. By measuring the strengths of absorption lines in stellar spectra, astronomers can estimate the abundance of elements such as iron, magnesium, silicon, calcium, nickel, and many others. Combined with stellar age and motion, chemistry can help identify stars that might share a common origin. Gaia adds extraordinarily precise measurements of stellar positions and motions, allowing researchers to search for candidates that could plausibly belong to the Sun's dispersed birth population. Simulations show, however, that galactic evolution spreads those siblings over large regions and makes simple orbital rewinding increasingly uncertain over billions of years. A star can match the Sun chemically and still be unrelated. It can move in a promising direction and still be a coincidence. It can have approximately the right age and still have formed somewhere else. To identify the actual former companion, astronomers would need an unusually convincing combination of evidence. At the moment, no such star is known. That absence does not prove the companion never existed. It also does not count as evidence that it did. It simply means the idea has to be tested indirectly, through the structure of the solar system and through models of what a temporary binary would have done. And this returns us to the period when the Sun and its possible partner were still together. A young star cluster provides the setting. A wide companion provides an additional gravitational influence. The planets are taking shape closer to the Sun. Beyond them lies a much larger population of icy planetesimals, scattered debris and material that has not yet been organised into the distant reservoirs we recognise today. This is where the companion stops being merely an interesting possibility about the Sun's family history. Its gravity begins to matter. If another star spent even part of the solar system's early development orbiting at hundreds or thousands of astronomical units, then every distant object was moving through a gravitational environment different from the one that exists now. Some orbits that would be stable around a solitary sun might behave differently. Some bodies could be scattered more efficiently, others might be captured. The outer edge of the Sun's influence could take on a different shape. Closer in, meanwhile, the developing planets still had to survive all of this. Jupiter was growing, Saturn was taking shape. Uranus and Neptune were interacting with a massive disk of smaller objects, and the giant planets would eventually migrate from the places where they first formed. Adding another star to that already complicated system raises an obvious question. How close could the companion come before it caused too much trouble? That condition is more restrictive than it first sounds. It is easy to add a second star to a drawing of the early solar system. It is much harder to add one to the physics and still end up billions of years later with Mercury, Venus, Earth, Mars, 4 giant planets, a Kuiper Belt, an Oort Cloud, and all the other small bodies still occupying recognisable parts of the system. A companion that came too close would cause serious trouble. A companion that stayed too far away would accomplish almost nothing. So the interesting version of the idea lives somewhere in between. The possible companion we have been discussing would have been very widely separated from the young Sun, perhaps around 1,000 astronomical units in one proposed model. That is more than 30 times Neptune's present distance from the Sun. At such a separation, the companion's gravitational pull on objects near Earth would be extremely weak compared with the Sun's. Out near the edges of the young solar system, however, the difference becomes much more important. This gives us a useful way to think about the system. Close to the Sun, almost everything behaves as though the Sun is in charge. Farther away, the companion begins to have a vote. Go farther still, and the entire stellar environment around the binary begins joining the meeting, whether anyone invited it or not. Gravity becomes a competition between several influences. Suppose you place a small rocky object near the orbit of Earth. The Sun's gravity dominates its motion so completely that a companion 1,000 astronomical units away is barely relevant. The object follows its orbit around the Sun, affected mainly by the Sun and, to a lesser extent, the planets. Now place the same object hundreds of astronomical units away. The Sun's grip is weaker there. The object's orbital period is much longer. Its speed is lower. A distant stellar companion can now make more noticeable changes to the shape and orientation of its orbit. Move the object still farther outward, into the region from which the Oort Cloud would eventually emerge, and those small gravitational disturbances can become major features of its history. This distance-dependent effect is one reason a wide binary is attractive as a hypothesis. It gives astronomers a possible way to alter the remote solar system without completely rebuilding the inner one. There is nothing mysterious about that. Gravity simply weakens with distance. If you double your distance from an object, its gravitational pull falls to 1/4 of what it was. At 10 times the distance, it is 1/100th as strong. That means a planet sitting close to the Sun feels a very different balance of forces from an icy body barely attached to the solar system, thousands of astronomical units away. The young planetary disk would therefore have contained different gravitational neighbourhoods. The innermost region was strongly controlled by the Sun. The middle region, where the giant planets formed, was still dominated by the Sun but vulnerable to interactions among the planets themselves. The outer disk contained smaller bodies whose future could be much more sensitive to the companion, passing stars and the gradual disappearance of the birth cluster. You can think of it as living near a railway line. If your house is several towns away, the train is technically part of the regional environment, but it probably isn't rattling your windows. Move your house beside the tracks, and suddenly the timetable becomes quite relevant. A companion star works in a similar way, except the timetable lasts several thousand years, and the train weighs roughly as much as the Sun. One immediate effect a companion can have is limiting the region around a star where long-term stable orbits are possible. Binary star dynamics have been studied extensively because we now know planets can exist in systems containing 2 stars. Numerical studies show that the stable region surrounding one member of a binary depends on several things, particularly the distance between the stars, their mass ratio, and how eccentric their orbit is. A close or highly eccentric companion reduces the amount of stable space available around either star. A distant companion leaves a much larger region essentially undisturbed. This matters because our possible solar companion cannot simply have any orbit we choose. Imagine that the second star had an extremely elongated orbit. For most of its journey it might remain far away. Then, every few thousand years, it could swing much closer to the Sun. Those close approaches would matter far more than its average distance. A binary whose stars remain 1,000 astronomical units apart on a nearly circular path is dynamically very different from one whose separation varies dramatically during each orbit. The closest approach, called the periastron, becomes particularly important. If the companion repeatedly approached the planetary region, it could disturb the disk, alter planetary orbits, or strip away material. So when we say the Sun may have had a companion at roughly 1,000 astronomical units, the number alone does not describe the whole system. We would also want to know the companion's mass, its orbital eccentricity, the orientation of its orbit relative to the Sun's disk, how long the pair remained bound, whether other stars changed that orbit before separating the pair, and unfortunately, the universe has misplaced the paperwork. Still, research on planets and disks in binary systems gives us some boundaries. Close stellar companions can truncate protoplanetary disks, effectively cutting off their outer portions and reducing the amount of material available for planet formation. Recent modelling of wide binaries finds that the effect becomes much less important as the stellar separation increases. In one set of simulations, equal mass companions separated by more than about 300 astronomical units allowed planet formation to proceed much more like it does around a single star, while companions much closer than that could substantially reduce disk size and the supply of material feeding growing planets. A companion around 1,000 astronomical units away therefore sits comfortably on the wide side of that comparison. That does not mean it would have no influence. It means the influence would be concentrated farther out. This is precisely what we need if we are trying to explain the modern solar system. Earth exists, Jupiter exists, Neptune exists. Whatever happened during the Sun's binary childhood cannot casually erase those facts. A useful hypothesis should leave the ordinary parts of the solar system mostly ordinary, while changing the places that remain difficult to explain, and there are plenty of those. The outer solar system contains objects whose orbits do not fit neatly into the simple picture many of us learned at school. The familiar planets mostly occupy nearly circular orbits in roughly the same plane. Beyond Neptune, the situation becomes much less organised. Some objects occupy resonances with Neptune. Others have strongly eccentric paths. Some are highly inclined. A few travel so far away that their orbits appear almost detached from the region dominated by Neptune. Then, much farther out, we expect the enormous population of the Oort Cloud. The Oort Cloud is not a thin disk like the planetary system. At great distances, it is thought to become approximately spherical, surrounding the Sun in every direction. That already tells us that something happened to objects that probably began life, much closer to the flattened plane where the planets formed. They were scattered outward. Their orbits were changed. Some became detached from direct planetary control. The gravitational effects of the surrounding galaxy and passing stars helped reshape their paths. A companion star could add another mechanism to that process. This is where its wide orbit becomes particularly useful. Imagine a young, icy body initially forming somewhere among or beyond the giant planets. It encounters Jupiter or Saturn. The giant planet changes its orbit, sending it outward. Usually scattering is not gentle. The small body might be sent into interstellar space and disappear from the solar system completely. Or it might enter a very elongated orbit, travelling thousands of astronomical units from the Sun before eventually returning toward the planets. That return creates a problem. If the object keeps coming back through the planetary region, another encounter with Jupiter or Saturn may eject it completely. To become a long-term member of the distant Oort Cloud, its orbit needs to change in a way that lifts its closest approach away from the giant planets. Passing stars and the galactic tide can do this. A temporary solar companion could potentially help as well. Its gravity could alter the distant portion of the scattered object's orbit, changing its angular momentum enough to raise its perihelion, the closest point of its orbit to the Sun. Once that closest point moves safely beyond the giant planets, the object is much less likely to be thrown out on its next visit. It has effectively been parked. Not neatly. Nothing involving cometary orbits is especially neat, but parked well enough to survive for billions of years. The 2020 proposal for an early solar binary was developed largely because a companion could increase the efficiency with which the young solar system retained or captured bodies in the outer Oort Cloud. In that model, an approximately equal mass companion at about 1,000 astronomical units could make the formation of the observed distant population more likely than it would be around an isolated Sun under the same assumptions. Notice what that means. The proposed twin is not mainly being asked to redesign Earth. It is being asked to help with the objects almost unimaginably far beyond Earth. That is a much more suitable job for a wide companion. There is another possibility too. Two stars moving together through the birth cluster create a different gravitational capture cross-section from one star travelling alone. An object drifting through the cluster that would normally pass the Sun and continue onward might lose enough energy during an interaction with the binary to remain trapped. This is a common feature of gravitational systems involving more than two bodies. With only two isolated objects, total orbital energy and angular momentum place strict limits on what can happen. Introduce a third body, and energy can be redistributed. One object can leave carrying extra energy, while another becomes more tightly bound. This is how three-body interactions can eject stars from clusters, change binary orbits, and capture objects into new systems. It is also one of the reasons three-body physics has a reputation for becoming complicated very quickly. Two bodies give you elegant ellipses, three bodies give you a computer. If the young sun and a companion formed a wide binary, passing planetesimals could interact with both stars. Under suitable circumstances, some objects belonging to the surrounding stellar environment might end up bound to the solar system. That raises an unusual possibility. Not every distant object orbiting the Sun would necessarily have formed from material that originally belonged to the Sun. Some might have been captured, perhaps from the general birth cluster environment, perhaps even from another young planetary system. The idea does not mean we have identified any particular object as stolen property. Astronomy is not currently issuing notices asking neighbouring stars to collect their missing comets. But capture is physically possible, and binaries can make it more efficient. The proposed connection to Planet 9 follows from this same reasoning. Planet 9 remains hypothetical. It has been proposed because some extremely distant trans-Neptunian objects appear to show patterns in their orbital orientations that could potentially be explained by the gravity of an unseen massive planet. Whether those patterns require another planet, result partly from observational biases, or have some other explanation remains under investigation. If a distant planet really does exist, one question would immediately follow. Where did it come from? It might have formed in our own solar system and later been scattered outward. It could have formed far from the Sun, though making a large planet at such enormous distances is difficult in conventional models. Or it could have been captured. The temporary binary model makes that final possibility more efficient. Siraj and Loeb argued that if Planet 9 were eventually shown to have a captured origin, an early binary companion would make such a capture substantially easier to produce. Their model also predicted that a binary capture scenario should leave additional distant dwarf planets on related kinds of orbits. That last point is particularly useful. A good hypothesis should try to do more than explain something we already know. It should risk being wrong. If a model predicts a population of distant objects and future surveys fail to find anything resembling that population, the model becomes less attractive. If the predicted objects appear in approximately the right numbers and orbital distributions, interest increases. That does not instantly prove the model, because several mechanisms can sometimes produce similar outcomes, but it gives astronomers something to test. The companion itself would also affect the Sun's ability to hold onto objects. A binary does not simply increase capture. Under other circumstances, it can increase losses. Some distant bodies could be pulled onto unstable paths and removed from the solar system. Others might pass close enough to the companion to have their orbital directions changed. A population that began as a relatively flat disk could gradually become thicker and more disordered. And because the companion itself would be moving, its effect would not point in one constant direction. The gravitational perturbation would vary throughout the binary orbit. This is where the length of the companion's stay matters. If the pair remain together for only a very short time, the companion might not have enough opportunity to create the structures we are discussing. If it survived for too long, especially after the Sun left the birth cluster, continued perturbations might produce effects that do not match what we observe today. The temporary nature of the model is therefore not an inconvenience added afterward. It is an important part of the mechanism. The companion needs enough time to matter. Then it needs to leave. One version of the scenario places the disruption of the binary within the Sun's birth environment. Encounters with neighbouring stars could unbind a pair separated by roughly 1,000 astronomical units, because wide binaries are relatively fragile. Once the companion escaped, the Sun would continue evolving as a single star, but the orbital changes produced during the binary phase could remain. That gives the solar system two different dynamical periods: an early period in which the Sun has a distant stellar partner, and the much longer period afterward in which it does not. This distinction is easy to overlook. When we look at the solar system today and simulate its behaviour, we naturally begin with the objects that are still here: the Sun, the 8 planets, known dwarf planets, asteroids, comets, other small bodies. But reconstructing the early system may require including objects that are no longer present. Planetary scientists already deal with this problem. The giant planets probably did not form exactly where they orbit today. Enormous populations of planetesimals were scattered or ejected. Some early planetary embryos collided with other planets or disappeared. The Moon itself is widely thought to have formed after a major collision between the young Earth and another planetary-scale body. The early solar system was full of participants who did not make it to the final photograph. A missing star would be a much larger version of the same problem. Naturally, adding a stellar companion makes the reconstruction more complicated. Scientists generally do not add extra objects simply because they make a story more interesting. The companion has to improve the explanation enough to justify introducing it. If ordinary stellar encounters, planetary migration, and galactic tides can reproduce the distant solar system perfectly well, there is little reason to insist on another star. If observations reveal structures that are substantially easier to produce with a temporary binary, then the hypothesis becomes more useful. This is why the outer solar system matters so much. The inner planets give us strong constraints on what the companion could not have done. The distant objects may tell us what it did. There's another subtle effect worth considering. Even a wide companion does not exist in isolation from the rest of the galaxy. Its own orbit around the Sun can be altered by passing stars and by the galactic gravitational field. Studies of very wide binaries show that external perturbations can change their stellar orbits over long periods, sometimes causing the companion's closest approach to its primary star to vary substantially. In mature systems, such changes can eventually destabilize distant planets. For the early Sun, surrounded by a denser stellar environment, this means a companion initially placed at a comfortable distance would not necessarily remain on exactly the same orbit. A passing star could make the binary more eccentric, another could widen it. A sufficiently strong encounter could break it. So the companion's influence on the solar system might have changed throughout its residence. At first, perhaps it remained far enough away to leave the planetary disk largely alone. Later, its orbit could become more eccentric. It might make one or several somewhat closer approaches, disturbing distant planetesimals more strongly. Then another stellar encounter could finally remove it. There are many possible histories. Most would not produce our solar system. The task is to find the small subset that could. This is why computer simulations become essential. No one can simply look at the equations for the Sun, a companion, 8 forming planets, thousands or millions of small bodies, passing stars, and a changing cluster environment, and calmly solve the entire history on paper. Even Isaac Newton might request a larger desk. Instead, researchers construct simplified models. They choose initial conditions. They assign masses and orbits. They allow the system to evolve numerically. Then they repeat the experiment many times, changing the starting conditions slightly. Perhaps the companion begins at 500 astronomical units, perhaps 1,000, perhaps 1,500. Perhaps the binary orbit is nearly circular, perhaps it is eccentric, perhaps the passing star comes from one direction, then another. Most simulated systems may fail to resemble ours. That is useful information too. If only a very narrow set of circumstances produces the observed solar system, the hypothesis becomes less probable. If a broad and physically natural range of conditions works, it becomes more appealing. For the companion hypothesis, one of the central challenges is preserving the known planets. We can be reasonably confident that the inner solar system did not experience a very close stellar encounter after the planets settled into stable orbits, because such an encounter would probably leave substantial dynamical damage. A wide binary companion is more promising because close planetary orbits can remain stable around one member of a sufficiently separated binary. Research on binary planetary systems has long shown that the stable zone around one star expands greatly as the binary becomes wider, and observational work indicates that companions beyond a few hundred astronomical units have much less effect on the formation of close-in planets than tighter binaries do. So Earth does not immediately rule out a lost twin. Neither does Jupiter. Neither does Neptune. The real question is more detailed. Would the exact architecture of the solar system still make sense? Could the companion coexist with the giant planets while they migrated? Could it affect the distant disk without erasing the populations we see in the Kuiper Belt? Would it leave too many objects in some regions and too few in others? Would its removal destabilize anything? Could the transition from binary sun to single sun happen naturally rather than requiring an implausibly perfect encounter? Those questions take us away from the simple image of two young stars sharing a birthplace. Now we have to watch what their gravity actually does. The planets were not finished objects quietly circling beneath the companion while everything happened safely in the distance. They were growing, migrating, scattering smaller bodies, and changing one another's orbits. Jupiter and Saturn in particular controlled enormous amounts of material through their gravity. Uranus and Neptune were probably not sitting exactly where we find them now. Place another star around that evolving planetary system, even a distant one, and there are several layers of gravitational interaction occurring at once. The companion pulls on the sun pulls on the companion. Both influence distant planetesimals. The growing planets scatter those planetesimals. The planets perturb one another. Passing stars disturb the binary. The birth cluster gradually disperses, and somehow, after all of that, the familiar planets have to emerge on orbits close enough to what we see today. That makes the next question much narrower than asking whether the Sun could have had a twin. How could a two-star childhood have shaped the planetary system that remained after one of the stars was gone? That question brings us into the region where the hypothetical companion has much less freedom to misbehave. The distant solar system can tolerate a surprising amount of gravitational rearrangement. The planets cannot. Mercury through Neptune occupy stable orbits today, and whatever happened during the solar system's early years had to leave behind a system capable of surviving for billions of years. So if the Sun really did spend part of its childhood with another star, that companion could not simply wander wherever it pleased. Its mass would matter. Its distance would matter. The shape of its orbit would matter. Most importantly, its closest approach to the Sun would matter. A companion sitting 1,000 astronomical units away most of the time sounds reassuringly distant, but if it followed a highly elongated orbit that brought it much closer every few thousand years, the planets would experience a very different gravitational environment. This is one reason astronomers studying planets in binary systems often pay close attention to the binary's eccentricity and periastron, the point where the stars come closest together. Long-term numerical studies of binary systems show a clear pattern. Planets can orbit one member of a binary quite safely if they remain sufficiently close to that star compared with the binary separation. Increase the companion's eccentricity, however, and the stable region around each star becomes smaller. The precise boundary depends on the masses and orbital configuration, but the general result is robust. A wide, relatively well-behaved companion leaves plenty of room for planets, while a closer or more eccentric one starts causing trouble. For an approximately equal mass binary, separated by something like 1,000 astronomical units, the familiar planets would sit deep inside the Sun's stable gravitational territory under many reasonable configurations. Neptune, the outermost major planet, averages only about 30 astronomical units from the Sun. That is still a long way from Earth, of course. Sunlight takes a little over 4 hours to reach Neptune, so calling it close requires the sort of perspective only astronomy can get away with. Compared with a companion 1,000 astronomical units away, however, Neptune is very close to the Sun. The Sun's gravity dominates. That means a sufficiently wide companion does not automatically throw Neptune away, drag Jupiter into an eccentric orbit, or send Earth drifting into interstellar space. If it did any of those things, we could dispose of the hypothesis rather quickly. The more subtle possibility is that the companion barely affects the planets directly, while changing the environment around them. That distinction matters. Planets do not form fully assembled, and then wait patiently for the gas and dust to clear. They grow inside a disk whose own structure changes with time. A stellar companion can influence that disk before it ever has the opportunity to disturb a completed planet. When two young stars orbit relatively close together, their gravity can strip or truncate material from the outer parts of their circumstellar disks. Observations and modelling of binary systems show that close companions can produce smaller disks and alter the conditions available for planet formation. Wider binaries are much less disruptive, and systems separated by hundreds of astronomical units can look considerably more like isolated stars from the point of view of their inner disks. For the Sun, that is good news. A companion at roughly 1,000 astronomical units would be far enough away that the main planet-forming disk could remain largely under the Sun's control. There would still be an outer limit beyond which the companion's gravity becomes increasingly important, but the region where the major planets formed could remain intact. Jupiter would have room to grow. Saturn could form. The ice giants could develop farther out. The rocky planets could continue their rather violent construction process close to the Sun. The basic ingredients of our planetary system would not require the companion's permission every morning. A much closer twin would create a very different story. Imagine placing another Sun at 50 astronomical units. That would put the companion only moderately beyond Neptune's present orbit. Now the gravitational architecture changes dramatically. The protoplanetary disk around our Sun would be much more strongly truncated. Material in the region where Uranus and Neptune formed could be severely affected. The companion could excite eccentricities and inclinations, alter the rate at which planetesimals collided, and make large parts of the outer disk unstable. Studies of planet formation in binaries with separations on the scale of tens of astronomical units find that the companion can heat and disturb the disk substantially, although the details depend on disk mass, stellar mass, and the binary orbit. That is not the companion we want. Our missing star works best as a distant participant, close enough to influence the outskirts, far enough away that the main planetary construction site can continue operating. Even without another star, that construction site was complicated enough. The giant planets almost certainly did not spend the entire history of the solar system sitting at their current distances from the Sun. Modern models of early solar system evolution generally involve substantial migration. Jupiter moved, Saturn moved, Uranus and Neptune moved. Their gravitational interactions with the gas disk, and later with huge populations of leftover planetesimals, exchanged angular momentum, causing their orbits to change. The details remain an active area of research, and there are several versions of the early instability scenario, but the basic idea that the giant planets underwent significant orbital evolution has become central to explaining many features of the outer solar system. One influential family of models began with the giant planets in a more compact arrangement than they occupy today. As they interacted with a massive disk of planetesimals, their orbits gradually shifted. Jupiter tended to move slightly inward, while Saturn, Uranus, and Neptune could migrate outward. Under some conditions, changes in the relationship between Jupiter and Saturn destabilize the outer system, producing encounters among the giant planets and scattering enormous numbers of smaller bodies. So even before we add a second star, the early solar system is not a quiet collection of planets following fixed circles. It is changing continuously. Neptune moves outward through a disk of icy material. Small bodies encounter Neptune and are thrown onto new trajectories. Some become trapped in orbital resonances, Some move inward and encounter the other giant planets. Others are thrown outward. A large fraction are eventually lost from the solar system altogether. Then, somewhere far beyond this activity, our possible companion is orbiting the Sun. Its direct pull on Neptune might be small, but it can alter the fate of material that Neptune sends outward. This gives us two connected gravitational systems operating at different scales. The planets control the inner scattering. The companion can influence what happens after objects travel much farther away. Imagine Neptune encountering a small icy body. The object passes close enough for Neptune's gravity to change its orbit. It is thrown outward onto a long elliptical path. Its closest approach may remain near Neptune, but its farthest point could now lie hundreds of astronomical units from the Sun. Near Neptune, the companion hardly matters. At the distant end of the object's new orbit, the situation changes. The Sun's pull has weakened. The object is moving slowly. The companion now has much more time and leverage to alter the orbit slightly. That alteration could change where the object returns. It might come back closer to Neptune. It might miss Neptune. It might be pushed onto an even larger orbit. It might eventually leave the system. Or its perihelion could be raised enough that it becomes partially detached from the giant planets. This is the sort of interaction that makes a wide binary interesting. The companion does not need to shove planets around directly. It can modify the consequences of what the planets are already doing. That is a much more delicate role. It is also much harder to detect billions of years later. If another star had dramatically changed Jupiter's orbit, we might see an obvious signature. If it merely changed the trajectories of thousands of small bodies that were already being scattered by Neptune, the evidence becomes mixed together with every other process operating at the same time. The resulting solar system is less like a clean experiment and more like a kitchen in which 6 people have prepared dinner at once. Something happened to the potatoes. Determining exactly who was responsible may require a simulation. Jupiter deserves particular attention because it dominates the planetary gravitational system. It contains more than twice as much mass as all the other planets combined. A small body sent toward the inner giant planet region has a good chance of eventually encountering Jupiter, and Jupiter is extremely effective at changing orbits. Some objects are redirected, some are captured temporarily, many are ejected entirely. In this sense, Jupiter has spent billions of years helping the solar system lose things. It is very good at it. That sounds destructive, but planetary systems naturally shed material as they evolve. The early solar system began with far more small bodies than we see now. The surviving asteroids, comets, Trojans, Kuiper Belt objects and other populations represent only part of the original inventory. A stellar companion could change the efficiency of that loss. An object scattered outward by Jupiter might normally escape. In a binary system, an interaction with the companion could alter the outcome. Another object that might otherwise remain loosely bound to the Sun could instead receive enough energy to escape. The companion is not simply a storage device for comets. It can both add and remove objects. This means researchers cannot test the hypothesis by asking only whether a companion produces more distant bodies. They need to examine the entire resulting distribution. Where do the objects end up? What are their eccentricities? What are their inclinations? How many survive? How many escape? Do the surviving populations resemble what we actually observe? And while all of this happens, the giant planets themselves must remain acceptable. Binary stability calculations give us confidence that planets close to one star can survive in sufficiently wide systems, but our solar system contains several massive planets that interact with one another. That makes the problem more complicated than testing a single Earth-like planet around one member of a binary. The companion can introduce slow gravitational changes called secular perturbations. These do not necessarily produce dramatic close encounters. Instead, weak gravitational effects accumulate over long periods, gradually changing orbital eccentricities or orientations. If the companion's orbit were significantly tilted relative to the planetary disk, Those long-term perturbations could alter the inclinations of distant objects. Under some configurations, a distant companion can drive large oscillations in eccentricity and inclination through mechanisms related to what are commonly called Kozai-Lidov cycles. The effect is most important when the geometry is right, and when other sources of orbital precession do not suppress it. For the major planets, their strong mutual interactions can reduce the ability of a very distant companion to produce extreme changes. For weakly bound bodies farther out, however, the companion has more opportunity. Again, we find the same pattern. The planets are relatively protected. The outskirts are not. There is also a useful clue in the spheral flatness of the solar system. The major planets orbit within a fairly narrow plane because they formed from the same rotating disk. Their orbital planes are not identical, but they are similar. If a stellar companion had repeatedly produced enormous inclination changes among the giant planets, today's system would probably look different. That gives researchers another constraint on the companion's allowed orbit. It cannot be merely distant. Its orientation and eccentricity must also avoid excessive excitation of the planetary system during the time it remains bound. The longer it stays, the more time weak effects have to accumulate. This creates another balancing act. A companion that disappears almost immediately cannot do much to the distant solar system. A companion that remains for hundreds of millions or billions of years has more opportunity to disturb structures we know survived. The proposed temporary companion therefore belongs mainly to the Sun's early birth cluster phase. It is present while distant reservoirs are beginning to form, and while capture from the surrounding environment is still possible. Then the cluster disperses. An encounter separates the stars, and the solar system continues most of its life around a single sun. The specific model proposed by Siraj and Loeb uses this temporary binary to increase the efficiency of forming the outer Oort Cloud and capturing very distant objects. This timing may also help separate the companion's influence from later planetary evolution. Once the twin is gone, Neptune can continue shaping the trans-Neptunian region under essentially the modern one-star configuration. The giant planets continue interacting with leftover planetesimals. Resonances move, objects are captured and released. The architecture of the Kuiper Belt develops. Some of those features can be explained without any binary companion at all. This is important because we should not give the lost twin credit for everything unusual beyond Mars simply because it makes a good suspect. Neptune alone is capable of producing remarkable structures. As Neptune migrated outward, its orbital resonances moved through the surrounding disk. Objects could become trapped in those resonances, changing their eccentricities and preserving relationships with Neptune that remain measurable today. Pluto is the famous example. Pluto crosses inside Neptune's orbital distance, yet the two do not collide because their motions are locked in a stable resonance. Pluto completes 2 orbits for every 3 made by Neptune. This is not a coincidence. It is part of a broader resonance structure beyond Neptune. Models involving Neptune's migration naturally populate several of these resonances and reproduce important parts of the observed Kuiper Belt. Simulations based on giant planet migration can account for much of the distant resonant and scattering population without requiring a second star. So what would the companion add? Not the basic existence of the Kuiper Belt, not Pluto's resonance, not every eccentric orbit beyond Neptune. Its effects should become more important where Neptune's direct influence begins to fade. That boundary is not sharp. An object can have a huge orbit and still encounter Neptune near perihelion. Another object might remain much closer overall, but be protected by resonance. Orbital dynamics refuses to arrange itself according to simple distance labels, just to make documentaries easier. Still, as perihelia rise farther from Neptune and semi-major axes become extremely large, conventional scattering by the known planets becomes less able to explain everything on its own. That is where early stellar encounters have long been considered. It is also where a temporary companion becomes potentially useful. One way to see the distinction is to imagine three objects. The first orbits at 40 astronomical units and repeatedly interacts with Neptune. For this object, Neptune is the main story. The second travels between 40 and several hundred astronomical units. Neptune may launch it onto that orbit, while external perturbations become more significant near its distant end. The third never comes remotely close to Neptune and spends most of its orbit hundreds or thousands of astronomical units away. Now the early birth environment matters much more. A passing star can influence it. The galactic tide can influence it once the orbit becomes large enough. A former companion could influence it. The farther outward we go, the more the solar system's history stops being only a story about planets. This is why the hypothetical twin is difficult to test using the major planets alone. If it occupied the right kind of wide orbit, the 8 planets might barely remember it. They would tell us mainly where the companion could not have been. Too close is bad, too eccentric may be bad, too inclined for too long could be bad, too massive at a small separation would be very bad. But a roughly stellar mass companion at a wide separation for a limited period can leave the familiar planetary region largely intact, while influencing material much farther away. Long-term stability studies of binary planetary systems are consistent with the broad possibility that planets close to one member of a sufficiently wide pair can survive. That may sound almost disappointing. We introduce another Sun and Earth barely notices. But this is actually one of the most important parts of the idea. A successful lost companion model should not require the modern solar system to look obviously binary. The companion is gone. Its strongest traces should remain in the places most sensitive to weak ancient gravitational influences. Those places are not near Venus. They are not in the asteroid belt. They may not even be close to Pluto. They are found among objects that travel far enough from the Sun that Neptune's control becomes intermittent, where orbits stretch across hundreds of astronomical units, and where a small change delivered billions of years ago can survive, long after the star that caused it has disappeared. Neptune therefore becomes our useful boundary marker. Once we move beyond Neptune, the solar system stops looking quite so much like the tidy diagram most of us first met in school. The 8 planets give the impression of organisation. Each travels around the Sun on a reasonably predictable path, and although their orbits are not perfect circles, they are close enough that a simple drawing can make the whole arrangement look almost architectural. Beyond Neptune, that neatness begins to break down. There are thousands of known icy bodies moving through this region, and they do not all behave in the same way. Some travel on fairly circular orbits. Some have eccentric paths that carry them much closer to the Sun at one end of their orbit than at the other. Some are tilted substantially relative to the plane of the planets. Some are locked into precise gravitational relationships with Neptune. Others repeatedly approach Neptune closely enough to have their orbits altered. Then there are objects that seem to have escaped Neptune's immediate control almost entirely. That variety makes the region beyond Neptune one of the most useful places to search for traces of the solar system's early history. It is also one of the easiest places to become confused, because the phrase Kuiper Belt is often used rather casually to describe almost everything icy and distant beyond Neptune. In practice, astronomers divide the trans-Neptunian population into several dynamical groups. The classical Kuiper Belt contains objects that generally orbit between roughly Neptune and the outer edge of the main belt, without undergoing strong present-day scattering encounters with Neptune. Some of these objects occupy what is called the cold classical population. Cold in this case does not mainly refer to temperature, although nobody is suggesting you bring a swimsuit. It refers to their relatively low orbital inclinations and eccentricities. These cold classical objects are especially interesting because their delicate orbital structure appears to have survived much of the violent rearrangement that affected the early outer solar system. Models of Neptune's migration have to be gentle enough or properly timed enough to preserve them. If Neptune had remained highly eccentric or highly inclined for too long while moving through their region, it could have excited or destroyed that population. Other objects are resonant. Pluto's the most famous example. It completes 2 orbits of the Sun for every 3 completed by Neptune. This 3-to-2 resonance keeps Pluto and Neptune in a stable gravitational rhythm, even though Pluto's eccentric orbit sometimes brings it closer to the Sun than Neptune. There are many other resonances farther out. Some objects make 1 orbit, while Neptune makes 2. Others follow more complicated ratios. These relationships are not just mathematical curiosities. They preserve information about Neptune's movement during the early solar system. As Neptune migrated outward, its resonances moved outward too, capturing objects along the way and altering their orbits. Some high perihelion objects located near particular resonances may even preserve evidence about how quickly Neptune migrated and when that migration ended. Then there is the scattering population. These bodies remain dynamically connected to Neptune. Their orbits may extend far beyond the classical Kuiper Belt, but their closest approaches still bring them near enough to Neptune that encounters can continue changing their paths over time. A scattering object can spend most of an orbit hundreds of astronomical units away, and still return eventually to the neighbourhood where Neptune gets another opportunity to interfere. Neptune is patient like that. It can wait several thousand years between appointments. Some scattering objects also become temporarily trapped in Neptune's resonances before leaving them again. Numerical studies suggest this temporary resonance sticking is common enough that scattering and transiently resonant objects should often be thought of as closely related populations rather than completely separate categories. All of this can happen with one sun. No twin required. That is an important point to establish before we start blaming a missing star for every strange object beyond Neptune. The known giant planets, especially Neptune, can produce an enormous amount of complexity on their own. Neptune can scatter objects. Its resonances can trap them. Interactions inside those resonances can raise their perihelia. Migration can leave objects stranded on fossilized orbits after a resonance moves elsewhere. In some cases, a body that once interacted strongly with Neptune can become detached enough that Neptune no longer controls it directly. Simulations have demonstrated several pathways in which resonant dynamics and residual Neptune migration create such detached objects near particular mean motion resonances. So the mere discovery of an object with an unusual orbit does not mean that another star must have passed through the solar system. But eventually we encounter objects that are difficult to place within this ordinary Neptunian machinery. Sedna is the classic example. Sedna was discovered in 2003 and its orbit immediately created a problem. Its semi-major axis is hundreds of astronomical units, meaning its full orbit extends enormously farther from the Sun than Pluto's. That alone is not particularly shocking. Neptune can scatter objects onto very elongated paths. The awkward part is Sedna's perihelion. Even at its closest approach to the Sun, Sedna remains roughly 76 astronomical units away. Neptune orbits at around 30. That means Sedna never comes remotely close enough to Neptune for an ordinary modern encounter to explain why its orbit looks the way it does. Something appears to have lifted Sedna's perihelion away from the giant planets. Once that happened, Sedna became dynamically detached. Neptune could no longer easily pull it back. And because Sedna spends most of its extremely long orbit much farther away, its current path may preserve information about processes that were operating when the solar system was young. Another object, 2012 VP113, reinforced the mystery. It also has a very distant orbit and an unusually high perihelion, near 80 astronomical units. Researchers studying Sedna, 2012 VP113, and related bodies have argued that at least some of these objects belong to an inner Oort Cloud population, rather than simply being ordinary members of Neptune's scattered disk. Modelling has found that objects with both very large semi-major axes and sufficiently high perihelia become increasingly difficult to generate through Neptune alone, and now our possible stellar companion becomes relevant again. A wide companion orbiting the young Sun could perturb objects that Neptune had already scattered outward. Imagine an icy planetesimal beginning somewhere beyond the giant planets. Neptune encounters it and changes its orbit. The object is launched onto an eccentric path whose closest point remains somewhere near Neptune, but whose farthest point reaches hundreds of astronomical units from the Sun. For most of its journey, nothing especially dramatic happens. Near the far end of the orbit, however, it is moving slowly, and the Sun's gravity is much weaker than it was near Neptune. If another star is orbiting the Sun at roughly 1,000 astronomical units, the planetesimal is now entering a region where that companion's gravitational pull becomes much harder to ignore. A relatively gentle perturbation can change the orientation of the object's orbit. It can alter the object's angular momentum. Most importantly, it can raise the perihelion. The body that once returned to Neptune might now miss Neptune completely. Its closest approach could shift from 35 astronomical units to 50, or 60, or farther. Once that happens, the object becomes much more difficult for the known planets to alter. The companion does not need to physically approach Sedna and fling it outward like a tennis ball. Gravitational dynamics generally works with less theatrical efficiency. Neptune can provide the initial scattering. The distant companion can modify the orbit later. Together they can potentially produce outcomes that neither would produce as efficiently alone. This sort of two-stage process is one reason the early solar system's outer regions are so difficult to reconstruct. When astronomers see one unusual orbit today, they may be looking at the combined result of several mechanisms. Neptune may have acted first. A stellar companion may have acted later. A passing cluster star may have added another perturbation. The galactic tide may have continued changing the orbit over billions of years. Trying to identify one culprit after all of that is rather like finding a dent in an old suitcase and determining which airport was responsible. There may have been several enthusiastic contributors. A lost companion is not the only stellar explanation for Sedna-like objects. Long before the temporary binary hypothesis was proposed, astronomers studied whether a passing star could have disturbed the young Kuiper Belt. During the Sun's residence in its birth cluster, close stellar encounters would have been much more likely than they are today. A sufficiently close flyby can raise perihelia, excite inclinations, strip material from the outer solar system, and potentially capture material from the passing star. Early simulations found that particular stellar encounters could produce Sedna-like orbits, and even suggested that, under some geometries, objects could be captured from another star's planetesimal disk. That gives us two related but distinct possibilities. One involves a star that passes once. The other involves a companion that remains gravitationally bound for some period. A flyby is brief. Its strongest influence occurs during one encounter. A companion can perturb objects repeatedly over many binary orbits. That difference matters because repeated weak perturbations can produce a different distribution of outcomes from one strong event. The companion also moves with the Sun through the birth cluster, which changes the system's ability to capture objects. A binary creates a more complicated gravitational environment in which energy can be transferred between the stars and passing small bodies. Under the early binary proposal, one major benefit of the companion is not simply disturbing objects that already belong to the Sun. It is improving the efficiency with which distant objects can be retained or captured. The original temporary binary model focused particularly on the outer Oort Cloud and on the possibility of capturing a distant planet, but it also predicts additional populations of remotely orbiting bodies that future surveys could test. We should be careful, though, not to turn Sedna into proof of a twin. It isn't. In fact, the more distant objects astronomers discover, the more tightly some early encounter scenarios can be constrained. A 2025 study examined whether close stellar flybys can reproduce not just Sedna's existence, but several properties of the growing population of high perihelion trans-Neptunian objects. The authors found that the required flybys become difficult to reconcile simultaneously with the observed low inclination tendency and proposed primordial orbital alignment, concluding that close encounters within about 1,000 astronomical units satisfying all of their constraints would be relatively unlikely. That result is a useful reminder of how science progresses. One object can make many explanations look possible. 10 objects begin causing problems. 100 can be downright inconsiderate. Every new distant body adds another orbital path that a successful model has to reproduce. The same principle applies to the Sun's possible twin. It is not enough to say that another star can disturb the Kuiper Belt. Of course it can. Put a star close enough and you can disturb almost anything. The real question is whether a physically plausible companion can produce the right amount of disturbance. It must preserve the cold classical Kuiper Belt. It must not ruin Neptune's resonant populations. It must allow the major planets to remain stable. At the same time, it should help explain the most detached and distant bodies. If we are going to include it at all, that is a much more demanding test. The outer edge of the classical Kuiper Belt adds another clue. The main concentration of classical objects drops sharply, beyond roughly the high 40s in astronomical units. This outer structure has motivated various explanations involving Neptune's migration, the original edge of the protoplanetary disk, and stellar encounters. A passing star can truncate a planetesimal disk if it comes sufficiently close, which made stellar flybys attractive as possible explanations for both the Kuiper Belt's edge and Sedna's unusual orbit. But once again, producing one feature is easier than producing all of them at the same time. If a star passes too close, it can overexcite the Kuiper Belt. Inclinations become too large. Too much material is removed. Dynamically cold populations are damaged. If the encounter stays comfortably far away, those populations survive, but Sedna may not receive enough of a perturbation. Nature does not give modelers many free lunches. A wide companion faces a related problem, although its effects are distributed over time rather than concentrated into a single flyby. Its orbital orientation matters. A companion whose orbit is almost aligned with the planetary disk produces different perturbations from one moving on a steeply inclined path. Its eccentricity matters. If it remains distant throughout its orbit, the disturbance can remain relatively gentle. If its orbit periodically brings it much closer to the Sun, its effect on the outer disk grows dramatically during each passage. Its mass matters too. A low-mass red dwarf at 1,000 astronomical units does not produce exactly the same history as another Sun-like star at the same distance. And then there is the length of time the pair remains together. Leave the companion in place for millions of years, and it has many opportunities to alter distant orbits. Remove it early, and some populations remain largely untouched. The challenge is to identify whether there is a range of parameters that produces the observed outer solar system without requiring an absurdly specific set of circumstances. This is where future surveys become particularly useful. Distant trans-Neptunian objects are extraordinarily hard to find. They are small, they are dark, they move slowly across the sky, and even when their orbits bring them relatively close to the Sun, relatively close can still mean billions of kilometers away. Most of the time, the most distant objects are far fainter than our surveys can detect. That creates severe observational biases. Astronomers naturally discover objects where telescopes look. They are more likely to detect an object when it's close to perihelion, and therefore brighter. Season, galactic background stars, telescope latitude, weather, survey strategy, and many other factors determine which parts of orbital parameter space are sampled well. This became particularly important when astronomers noticed apparent clustering in the orientations of some extremely distant trans-Neptunian objects. That clustering helped motivate the Planet 9 hypothesis. If several distant objects have orbits pointing in related directions, perhaps the gravity of an unseen planet is organizing them. But carefully characterized surveys such as OSSOS demonstrated that discovery biases for large semi-major axis objects can be surprisingly strong. Its detected sample was consistent with an underlying population, having uniformly distributed orbital orientations, meaning the observed clustering cannot simply be treated as an unbiased map of what exists beyond Neptune. This uncertainty affects our lost companion too. Suppose a temporary binary predicts that distant objects should have a particular distribution of inclinations or perihelia. We cannot compare that prediction directly with a list of discovered objects without accounting for where and how those objects were found. The survey has to be simulated as carefully as the solar system. If a telescope was never capable of detecting certain orbits, the absence of those orbits in the catalogue tells us very little. Outer solar system astronomy therefore involves an unusual combination of celestial mechanics and detective work. First you calculate what the model produces, then you calculate which of those objects your telescope would have noticed. Only then can you compare the result with reality. That process is gradually improving as larger, deeper, more systematic surveys increase the sample, and the lost companion hypothesis gives us something useful to look for. If a binary sun captured or substantially rearranged a population of distant objects, the resulting orbits should not be completely arbitrary. Their semi-major axes, perihelia, inclinations and angular orientations carry information about the geometry of the original interactions. Different formation mechanisms predict different statistical patterns. A passing star may produce one distribution. Neptune plus galactic tides may produce another. A distant planet acting for billions of years may produce another. A temporary stellar companion may produce another. None of these predictions is likely to label itself conveniently, but enough objects can make the differences measurable. There is an especially interesting transition as we move outward from the classical Kuiper Belt. Around 40 or 50 astronomical units, Neptune's migration and resonances dominate much of the structure. At 100 astronomical units, Neptune can still matter enormously for objects whose perihelia return near the planet. At several hundred astronomical units, objects with high perihelia begin preserving information that is increasingly difficult to obtain from Neptune alone. Then, at thousands of astronomical units, we enter a regime where galactic tides and passing stars become central to the long-term behaviour. The solar system does not have one clean boundary between planet-controlled and star-controlled space. The balance changes gradually. That gradual change is exactly where the possible twin could have left its most useful fingerprints. Not by carving a giant symbol into the Kuiper Belt, not by arranging every distant object into one obvious pattern. More likely, it would change probabilities. More objects might reach high perihelia. More material might survive at large distances. Some objects that otherwise escaped might remain bound. Others could be captured from outside. Certain inclination distributions might become more common, and after the companion disappeared, those bodies would continue orbiting a sun that was now alone. The Kuiper Belt we observe today would then contain only part of the record. Its inner populations would mainly preserve the history of Neptune's migration and the giant planets. Its most distant members might also preserve the birth cluster. And farther beyond those objects lies an even larger reservoir where the lost companion, if it existed, could have been far more influential. The Oort Cloud is where the scale of the solar system becomes difficult to picture. Neptune is already extremely distant from us. It orbits about 30 astronomical units from the Sun, which means roughly 30 times the average distance between Earth and the Sun. Pluto travels somewhat farther. Many trans-Neptunian objects reach hundreds of astronomical units on elongated paths. The Oort Cloud extends the discussion much farther. Astronomers generally think of it as a vast reservoir of icy bodies surrounding the solar system, at distances ranging from thousands to tens of thousands of astronomical units. Its outer regions may extend a significant fraction of the way toward the nearest stars. We have never taken a photograph showing the entire cloud. It is far too diffuse, dark, and distant for that. Its existence is inferred mainly from long-period comets, whose orbits indicate that they have arrived from extremely remote parts of the solar system. A comet can spend millions of years far from the Sun, moving slowly through darkness, before something alters its orbit enough to send it inward. Then, suddenly, At least by astronomical standards, it appears in the planetary region. Sunlight heats its surface. Frozen material begins turning into gas. Dust is released. A coma forms around the nucleus, followed by a tail that can stretch for millions of kilometers. People on Earth look up and see a bright comet. The spectacular part lasts weeks or months. The journey that produced it may have taken longer than our species has existed. The obvious question is how so many objects ended up that far away in the first place. The Sun's planet-forming disk probably did not extend as a dense supply of solid material all the way to 50,000 astronomical units. The objects associated with the Oort Cloud are thought to have formed much closer to the Sun and then been transported outward. The giant planets provide the first part of the mechanism. During the early solar system, Jupiter, Saturn, Uranus and Neptune interacted with enormous numbers of leftover planetesimals. A small, icy body passing near one of the giant planets can receive a gravitational kick. The planet does not need to touch it. As the small body falls into the planet's gravitational field and swings around it, energy and angular momentum can be exchanged between the two orbits. Because the planet is enormously more massive, its own orbit changes by an almost imperceptible amount. The planetesimal can change dramatically. Some objects were thrown inward, some moved outward. Many were ejected from the solar system entirely. Jupiter in particular is very effective at producing escape trajectories, but not every scattered body escapes immediately. Some are placed on huge elongated orbits that remain gravitationally bound to the Sun. Imagine an object that starts among the giant planets and is scattered outward until the far end of its orbit lies several thousand astronomical units away. It has not yet become a secure member of the Oort Cloud. Its problem is the other end of the orbit. If its perihelion still passes through the giant planet region, then eventually it comes back. Perhaps not for thousands of years, but it returns, and when it does, Jupiter or Saturn may interact with it again. After several encounters, the most likely result is often complete ejection. For an Oort Cloud object to survive, something needs to change its orbit before the planets get another opportunity to remove it. This is where outside gravity becomes useful. At thousands of astronomical units from the Sun, an object's motion is much more sensitive to gravitational influences that are insignificant near Earth. Passing stars matter. The gravitational field of the Milky Way matters, and during the solar system's earliest period, the surrounding birth cluster mattered. These external forces can slowly alter the orientation and shape of an object's orbit. Most importantly, they can raise its perihelion. An object that once returned to the neighbourhood of Jupiter may have its closest approach shifted outward. Now it no longer crosses the dangerous planetary region. The giant planets cannot easily eject it. The object has effectively been separated from the machinery that originally threw it outward. Over time, large numbers of bodies can be stored in this way. That is the basic logic behind Oort Cloud formation. The planets throw objects outward. External gravitational influences help prevent some of them from coming all the way back. It sounds almost coordinated. It isn't. Nobody planned the arrangement. It is simply the result of different gravitational influences becoming important at different distances. Numerical simulations of Oort Cloud formation have shown that the Sun's early stellar environment can strongly influence this process. In models where the young solar system spends time inside an open cluster, stellar encounters can populate the inner Oort Cloud efficiently, leaving a long-lived record even after the Sun exits the cluster and spends billions of years in the much quieter galactic environment we know today. Now add the possible companion. Instead of one sun moving through the birth cluster, we have two stars gravitationally bound to one another at a wide separation. The companion may orbit at something like 1,000 astronomical units. That puts it in a particularly interesting position. It is much too distant to dominate the planets. but it sits directly within the region through which scattered planetesimals must travel on their way toward the distant Oort Cloud. For those objects, the second star is not a minor detail. Suppose Neptune scatters an icy body outward. Its new orbit reaches several hundred astronomical units. The companion perturbs it. Perhaps the perihelion rises slightly. Perhaps the semi-major axis changes. Another interaction occurs during a later orbit. Then a passing cluster star adds another disturbance. The object might eventually settle onto an orbit that would have been much more difficult to reach around a single sun. Another body experiences the opposite. The companion gives it additional energy and it escapes completely. A third object may not have originated around our sun at all. It may have approached from elsewhere in the birth cluster. Now the binary nature of the system becomes especially useful. Capturing an unbound object around a single isolated star is difficult. If an object approaches the sun from interstellar space, it normally accelerates as it falls inward, swings around the sun, and departs again with essentially the same total orbital energy it had before. Gravity speeds it up on the way in and gives the energy back on the way out. There is no convenient brake pedal. A binary changes that. With two massive bodies moving around one another, energy can be redistributed during an encounter. A passing object can interact with both stars. Under the right circumstances, one component of the system takes away some of the object's orbital energy. The object that arrived unbound can leave the encounter bound to the binary. Three-body interactions make capture much easier. It is the same broad reason that complex gravitational systems can exchange objects, eject stars, or radically rearrange orbits without requiring a collision. Energy moves between participants. The bookkeeping still works. It simply becomes considerably more interesting. This increased capture efficiency is one of the main motivations behind the proposed early solar binary. Suraj and Loeb argued that a temporary approximately equal mass companion at roughly 1,000 astronomical units could increase the likelihood of producing the observed outer Oort Cloud population, compared with an isolated sun evolving under the same birth cluster conditions. That does not mean astronomers have counted every object in the Oort Cloud and discovered exactly the number predicted by a binary model. We do not know the Oort Cloud nearly well enough for that. Its objects are too faint and too distant to inventory directly. Researchers infer its population statistically from the comets that enter the inner solar system, and those estimates depend on assumptions about comet brightness, size distributions, orbital evolution, fading, disruption, and observational selection. In other words, counting the Oort Cloud is a little like estimating the population of an enormous country by interviewing the occasional person who happens to wander through your garden. It can be done. There are uncertainties. What matters for the binary hypothesis is that models of Oort Cloud formation sometimes have difficulty trapping enough material at very large distances efficiently. A companion star can improve the capture cross-section of the young solar system and change how material becomes stored. But there is another side to this. A companion can also remove objects. Put a star close enough to a cloud of loosely bound comets, and it does not politely sort them into stable storage. Some are disturbed onto more tightly bound orbits, some are redirected, some are sent toward the inner solar system, others are stripped away. A successful model therefore has to produce the right balance. The companion cannot merely increase every population indefinitely. It has to create something resembling a cloud that can later survive the loss of the companion and another 4.5 billion years of galactic evolution. This is where the distinction between the inner and outer Oort Cloud becomes useful. The inner Oort Cloud is more tightly bound to the Sun. Its objects occupy smaller orbits than those in the outermost reservoir. They are still extremely distant by planetary standards, but the Sun's gravity holds them more securely. The outer Oort Cloud is more vulnerable. Passing stars can change it. The galactic tide can change it. A close enough encounter can remove some of its objects completely. These outer bodies are also the ones more easily redirected toward the planetary region, which is why they are often associated with the supply of observable long-period comets. The Sun's birth cluster could have been particularly important for constructing the inner cloud. Simulations in which the young Sun spends its first tens or hundreds of millions of years in a cluster have found that frequent early stellar encounters can trap objects much closer to the Sun than the weaker galactic environment can later accomplish. Much of this early trapped population can then remain stored for billions of years after the cluster disperses. A binary companion would modify that early period again. Now there are passing cluster stars, two bound stars, the giant planets, and thousands upon thousands of small bodies moving through all of their gravitational fields. The resulting histories can become extremely complicated. An object might be scattered by Saturn, then Uranus, then Neptune, then the companion, then a neighbouring star, after which it spends 4 billion years doing almost nothing interesting at all. From the object's point of view, this is probably ideal. For the astronomer trying to reconstruct its childhood, it is less convenient. There is also the possibility of exchange between the Sun and its companion. If both young stars possessed planetesimal disks, interactions at large distances could transfer material from one system to the other. Some comets around the Sun could therefore in principle contain material that condensed in the disk around the companion. The reverse could also happen. The twin might leave the birth cluster carrying objects that originally formed around our Sun. If that sounds strangely personal, remember that the objects involved are mostly frozen mixtures of rock, dust and volatile compounds. They are unlikely to demand visitation rights, but scientifically, captured material would be fascinating. Objects formed around different stars may begin with different chemical compositions, isotopic ratios, or thermal histories. In theory, sufficiently unusual chemistry in a primitive object could provide clues that it formed in a different protoplanetary environment. In practice, proving that would be extremely difficult because the solar system itself already contained substantial chemical variation. Still, the possibility reminds us that a binary solar system would not merely have been a one-star planetary system with an extra lamp in the distance. The two systems could exchange material. They could alter one another's outer reservoirs, and when they separated, each star might carry away a mixture of objects from their shared early environment. The moment of separation would matter as well. Suppose the companion remains bound while the earliest Oort Cloud is taking shape. Then another star passes nearby in the birth cluster and disrupts the binary. The twin escapes. What happens to the objects that were orbiting within the combined gravitational environment? Some remain attached to our Sun, some may leave with the companion, some may be lost altogether. The removal of the companion changes the gravitational potential of the system, but not every orbit instantly falls apart. Objects that are already securely bound to the Sun can continue orbiting it. The details depend on where each body is, how quickly the stellar separation occurs, and the geometry of the encounter that breaks the binary. In that sense, the breakup itself may help shape the final cloud. The binary phase builds and rearranges a population. The disruption freezes part of that structure into a new one-star configuration. Then the remaining solar system continues evolving under passing field stars and the galactic tide. Those later influences never stop. Even now, stars pass through the Sun's broader neighbourhood. Most remain comfortably distant. Over millions of years, however, their gravitational effects on the outer Oort Cloud matter. The Milky Way also produces a persistent tidal field because the solar system is orbiting inside the gravitational potential of the galactic disk. These forces slowly alter distant cometary orbits. Sometimes a comet's perihelion is lowered enough that it begins falling toward the planets. After spending an extraordinary amount of time beyond the visible solar system, it enters the region near Saturn and Jupiter. At that point, several things can happen. Jupiter may eject it. It may pass around the Sun and disappear again. It may fragment. Or it may become one of the long-period comets we observe from Earth. This makes every long-period comet a messenger from a part of the solar system we cannot visit easily. Its present orbit tells astronomers something about the reservoir from which it arrived. Its composition preserves information about primitive material. But even with those messengers, reconstructing the exact structure of the Oort Cloud is difficult. because the journey inward alters their trajectories. Planetary encounters modify them. Stellar encounters can modify them before they arrive. The galactic tide has already been working on them. We are rarely seeing an untouched record. That is why researchers rely so heavily on large numerical populations, rather than trying to explain individual comets one at a time. Create millions of test particles, scatter them with the giant planets, add the galactic tide, add passing stars, place the solar system inside a birth cluster, then compare how many particles become trapped, where their perihelia end up, how long they survive, and how often they return toward the inner solar system. The binary hypothesis simply adds another major ingredient to that experiment. Run one simulation with the Sun alone, run another with a wide companion, keep the other assumptions as similar as possible, then ask whether the binary version produces the distant populations more naturally. That comparison is what made the temporary companion interesting in the first place. In the 2020 model, the binary increased the likelihood of forming the outer Oort Cloud population and also increased the efficiency of capturing a hypothetical distant planet. And this brings us back to Planet 9. Not because the Oort Cloud requires Planet 9. It does not. And not because Planet 9 has been discovered. It has not. The connection is that both problems concern the very distant gravitational history of the solar system. If a large planet exists hundreds of astronomical units from the Sun, astronomers would need to explain how it reached that orbit. One possibility is that it formed closer in and was scattered outward. Another is capture. A binary sun would make capture more efficient. That same binary could also capture smaller dwarf planet-sized bodies. So the hypothesis produces a testable expectation. If the solar system captured one substantial distant object during its binary phase, there may be others occupying related remote regions. The original binary model specifically predicted an enhanced population of distant dwarf planets that future wide-field surveys could potentially detect. That is much more useful scientifically than simply saying, perhaps there was another star. A missing object is difficult to prove. A predicted population can be searched for. If astronomers discover many distant bodies with orbital properties compatible with capture in an early binary, the model becomes more interesting. If increasingly complete surveys show that the predicted population is not there, that weakens the idea. Either result teaches us something. The Oort Cloud therefore acts less like direct evidence for the Sun's twin and more like a testing ground. We cannot point to one comet and say it belonged to the companion. We cannot measure the cloud and find a visible indentation where another star once sat. What we can do is compare populations. How efficiently does a lone sun build the cloud? How efficiently does a binary sun build it? What does a birth cluster contribute? Which parts of the cloud survive? What fraction of objects are captured rather than formed locally? What orbital distributions result after the binary is disrupted? And do those distributions match the distant bodies we eventually observe? Those questions become especially interesting because the boundary between the inner Oort Cloud and the most remote trans-Neptunian objects is not completely clean. Sedna and similar bodies sit in an intermediate region. They are far beyond ordinary Kuiper Belt dynamics, but much closer than the traditional outer Oort Cloud. Their orbits may preserve evidence of the same early gravitational processes that constructed the inner cloud. A stellar encounter capable of creating Sedna-like objects could also help populate the inner Oort Cloud. A binary companion could influence both. A captured distant planet could influence some of those bodies for billions of years afterward. Several explanations therefore begin overlapping in the same part of space. That overlap is not merely an inconvenience. It gives us a way to test them against one another. A model that explains the Oort Cloud but produces the wrong detached objects has a problem. A model that explains Sedna but destroys the cold classical Kuiper Belt has a problem. A model that captures Planet 9 but predicts dozens of other large bodies that surveys eventually fail to find has a problem. The solar system does not allow us to choose one interesting feature and ignore everything else. Every successful early history has to produce all of them together. That requirement becomes particularly demanding when we examine the small collection of objects occupying the strangest known orbits beyond Neptune. Some have perihelia too distant for ordinary Neptune scattering. Some travel hundreds of astronomical units away. Some appear, depending on how observational biases are handled, to show patterns in orbital orientation. They have inspired proposals involving passing stars, early cluster dynamics, migrating planets, an unseen massive planet, and combinations of several mechanisms. If the Sun's twin really did spend part of its youth near the outer edge of the developing solar system, these strange distant bodies are among the places where its gravitational fingerprints might have survived. The farther we travel beyond Neptune, the less useful the familiar picture of the solar system becomes. There is still one sun, of course, and everything remains governed by gravity. But the arrangement of objects becomes increasingly difficult to explain, with a simple sequence of planets followed by a belt of icy debris. Some of the bodies out here travel on orbits so large that one journey around the Sun takes thousands or tens of thousands of years. Their paths can be extremely elongated. At their closest point, they may still remain far beyond Neptune. At their most distant point, they can reach hundreds or even more than 1,000 astronomical units from the Sun. These objects are interesting for a simple reason. If Neptune cannot get close enough to them now to produce their unusual orbits, then something else must have happened. Perhaps Neptune influenced them long ago, when the solar system was arranged differently. Perhaps another planet is still influencing them. Perhaps a passing star altered their paths. Perhaps the Sun's birth cluster played a role. Or perhaps during the first part of the solar system's history, another star was orbiting the Sun and quietly changing the trajectories of objects that ventured far enough away. The most famous of these distant worlds is Sedna. Sedna spends its entire orbit well beyond Neptune. Its closest approach to the Sun is roughly 76 astronomical units, more than twice Neptune's distance. Its farthest point lies hundreds of astronomical units farther out. That perihelion is the important part. Neptune is extremely good at scattering small bodies when they pass nearby, but Sedna never does. If you try to explain Sedna by starting with its present orbit and using only the present-day giant planets, you would quickly run into a problem. Neptune cannot simply reach across more than 40 astronomical units and give Sedna the sort of strong gravitational encounter required to place it there. So Sedna appears to preserve evidence of an earlier event. It is less like a normal member of the Kuiper Belt and more like a surviving record from a period when the outer solar system experienced gravitational conditions that no longer exist. Then, astronomers found another object that made the situation more interesting. 2012, VP113 also has a very high perihelion, around 80 astronomical units. Like Sedna, it remains far beyond the strong direct gravitational influence of Neptune throughout its orbit. The existence of two such bodies immediately made it harder to dismiss Sedna as an isolated oddity. Then came 2015 TG 387, now officially named Leleakuhonua. Its orbit is even larger. Its semi-major axis is around 1,170 astronomical units, although orbital parameters for such distant bodies improve as observations accumulate. Its perihelion is roughly 65 astronomical units from the Sun, again keeping it far from Neptune's strongest influence. The Discovery paper described it as another member of the inner Oort Cloud population, alongside Sedna and 2012 VP113. One orbit like this is curious. Several begin to form a population, and populations are much more useful to astronomers than individual curiosities, because a population allows you to ask statistical questions. Do these bodies share similar inclinations? Do their perihelia occupy a particular range? Do the long axes of their orbits point in similar directions? Are they clustered in ways that random orbits should not be? How many similar objects should exist that we have not found yet? Different origin stories can give different answers. A passing star might produce one pattern. An early binary companion might produce another. A distant massive planet acting over billions of years could produce another. Neptune's early migration, combined with the galactic tide and the Sun's birth cluster, could produce still more. The difficulty is that astronomers are trying to reconstruct a complicated event using a very small sample. These objects are exceptionally hard to discover. Take Leleku-Honua. Its orbit extends to such enormous distances that it spends most of its time far beyond the point where present surveys have much chance of detecting it. We found it because it happened to be in the comparatively small portion of its orbit where it was bright enough to notice. That creates a major observational problem. Suppose there are 1,000 distant objects whose orbits point in every possible direction. A telescope survey does not observe the entire sky equally. Some areas are visible during certain seasons. Some regions contain dense backgrounds of galactic stars that make faint-moving objects harder to detect. Some parts of the sky receive deeper observations than others. Weather affects observing schedules. Different telescopes operate from different latitudes. The result is that the dozen objects we actually discover may appear clustered, even if the 1,000 objects from which they came are not. This issue became particularly important after astronomers noticed that several extreme trans-Neptunian objects seem to have similarly oriented orbits. That apparent alignment is one of the observations that led to the modern Planet 9 hypothesis. The basic argument is that if a planet several times the mass of Earth were orbiting hundreds of astronomical units from the Sun, its long-term gravity could organize the orbits of distant small bodies. Instead of pointing in random directions, some of their elongated orbits could become confined into preferred orientations. The idea is attractive because one unseen planet can potentially explain several unusual populations at once. It can produce high perihelion objects. It can influence extreme inclinations. It can generate long-period Neptune-crossing bodies. Recent dynamical work has continued to argue that some observed trans-Neptunian populations fit simulations containing Planet 9 better than simulations without it. A 2024 study, for example, examined long-period, low-inclination Neptune-crossing objects and reported that a Planet 9 model reproduced their distribution substantially better than the comparison model without the planet. But Planet 9 remains hypothetical. No telescope has yet produced an accepted direct detection of the planet, and the orbital clustering argument remains debated because survey selection effects can be extremely strong. The Outer Solar System Origin Survey, or OSSOS, carefully recorded where it looked and how sensitive each observation was. When researchers applied those known observational biases to the distant objects found by the survey, they found that the detections were compatible with an underlying population whose orbital directions were distributed uniformly. Another analysis combining well-characterized surveys similarly concluded that its sample did not provide statistically significant evidence for orbital clustering. This does not prove Planet 9 is absent. It means the evidence is more complicated than looking at a diagram and noticing that several orbital lines appear to point the same way. Outer solar system diagrams are very good at making arguments look obvious. Statistics is very good at making them less comfortable. That is healthy. Planet 9 should be tested through several independent predictions rather than depending on one apparent pattern. The same standard applies to the Sun's lost companion. We should not look at Sedna, draw a second star on a diagram and declare the mystery solved. A companion star is one possible early influence. The question is whether it explains several features naturally, and whether it predicts things that astronomers can eventually check. There is an important difference between Planet 9 and the hypothetical solar twin. If Planet 9 exists, it should still be here. Its gravity would be affecting distant objects right now. The Sun's companion, by contrast, would have acted only during the early solar system. Its effects would be fossilized into populations that continued evolving after the star disappeared. That gives the two hypotheses very different roles. The lost companion is an ancient disturbance. Planet 9 would be an active one, and there's no reason they have to be mutually exclusive. In fact, one version of the binary hypothesis connects them directly. If the young Sun had a wide stellar companion, the pair would have been better at capturing objects from the surrounding birth cluster than a single Sun would have been. That includes small bodies, but it could also include something much larger. The 2020 early binary model proposed that if Planet 9 exists, and if it was captured rather than formed around the Sun, a temporary stellar companion could make that capture substantially more likely. The same model predicts that such a capture process should also leave an enhanced population of distant dwarf planets on broadly similar kinds of orbits. This creates an interesting chain of possibilities. Perhaps the Sun had a companion. Perhaps the binary captured distant objects. Perhaps one of those captured objects was a planet. Perhaps that planet remained after the companion escaped. Then, for the next several billion years, the captured planet continued rearranging smaller bodies. If that happened, some of the strange orbits we observe today would not be direct fingerprints of the twin. They would be fingerprints of something the twin helped leave behind. There is a certain efficiency to that scenario. The companion appears early, changes the solar system's ability to capture objects, then disappears. A captured planet remains and continues doing the gravitational work. But we should notice how many uncertain statements were required to get there. The Sun may have had a companion. Planet 9 may exist. Planet 9 may have been captured. The binary may have enabled that capture. Each step has to be tested independently. Stacking several possibilities together can produce an elegant story, but elegance is not the same thing as evidence. Astronomers therefore keep looking for additional distant bodies. Every new orbit adds information. Suppose surveys discover many more Sedna-like objects, but their orbital directions are completely random. That would weaken explanations relying strongly on persistent orbital alignment. Suppose instead that a much larger, carefully characterized sample shows statistically convincing clustering, even after observational biases are included. That would strengthen the case that some long-lived gravitational influence is organizing them. Suppose astronomers find a population of very distant dwarf planets resembling what binary capture models predict. That would make an early companion more interesting. Suppose they do not. That would place stronger limits on the model. This is one reason the next generation of our outer solar system surveys matters so much. For decades, astronomers have been working with a tiny census of extreme objects. The underlying population could be a sormus. Likuhonua's discovery team estimated that there may be around 2 million inner Oort Cloud objects larger than roughly 40 kilometers if the observed size and orbital distributions can be extrapolated. That estimate carries large uncertainties, but it demonstrates how misleading the handful we have detected may be compared with the unseen population. Finding more objects does more than increase the catalogue. It reveals the shape of the population. That shape can preserve ancient gravitational events. Consider inclination. If some process strongly disturbed the outer solar system, we might expect it to produce objects on highly tilted or even retrograde orbits. A gentle process could preserve a lower inclination population. A stellar encounter from one particular direction might leave a different inclination signature from a long-lived distant planet. A binary companion with a particular orbital plane could affect distant bodies differently again. Perihelion distance provides another clue. There is a major dynamical difference between an object whose perihelion sits at 35 astronomical units and one whose perihelion sits at 80. The first can still interact strongly with Neptune, the second cannot. If surveys reveal a continuous distribution between those populations, one family of mechanisms may work well. If there is a pronounced gap, another might be preferred. Semi-major axis also matters. An object reaching 200 astronomical units is exposed to a different balance of forces from one reaching 2000. As the orbit expands, passing stars and galactic tides become increasingly important. A former companion could dominate certain regions during the solar system's early history, but have very little effect elsewhere. Then there are orbital angles. These are the quantities at the centre of the clustering debate. Every elongated orbit has an orientation. If many distant bodies share a preferred orientation that cannot be explained by survey bias, something may be maintaining that pattern. Without an active perturber, orbital orientations tend to precess over long periods. That makes a persistent alignment especially interesting because a disturbance that occurred 4.6 billion years ago might not remain neatly aligned forever. This gives us a way to distinguish ancient and continuing influences. A lost companion can create an initial distribution. A surviving distant planet can maintain a distribution. Passing stars can periodically disturb it. The galactic tide can modify it. When researchers build full numerical models, all of these processes may need to be included. That is why the distant solar system is not likely to yield one simple clue reading. Second star was here. Instead, astronomers look for combinations of evidence. Sedna tells us that something can lift objects far beyond Neptune's reach. 2012 VP113 tells us Sedna is not unique. Leliaku-Honua shows that objects can occupy extraordinarily large detached orbits and remain stable over very long periods under the known planets. Its evolution can still be affected by stellar encounters, which is exactly what we would expect for an object spending so much time at immense distances. Other extreme trans-Neptunian objects add information about inclinations, resonances, perihelia, and orbital orientations. Each one narrows the number of histories capable of producing the whole population. A close stellar flyby is one candidate history. A temporary binary is another. Planet 9 is another. Early planetary migration is certainly part of the story. The Sun's birth cluster almost certainly contributed some gravitational perturbations. The eventual answer may combine several of them, rather than selecting one. This becomes especially clear if we imagine what would happen immediately after the companion disappeared. The star leaves, but nothing in the outer solar system resets. A Sedna-like object remains on whatever orbit it had at that moment. Captured bodies remain captured if they are sufficiently bound to the Sun. The Oort Cloud continues developing. Neptune continues influencing bodies that come near it. Passing stars keep producing occasional perturbations. The galaxy keeps applying its slow tidal influence. If a distant planet was captured, it keeps orbiting. The solar system simply continues from the conditions produced by its binary childhood. 4.5 billion years later, astronomers arrive with telescopes and try to work backward. This is the difficult part of using distant orbits as clues. We are not looking directly at the event. We are looking at what survived everything that happened afterward. Some evidence has been erased. Some has been altered. Some objects have been ejected. Others may have entered the system later, and the few objects we have detected represent a strongly biased sample of a population that is mostly invisible. Yet these distant worlds may still provide one of our best opportunities to test the twin hypothesis, because the major planets were too deeply protected by the Sun's gravity to record much of the companion's presence. Earth probably remembers almost nothing about the twin. Sedna might. The inner Oort Cloud might. A captured distant planet, if one exists, could. The population of yet undiscovered objects beyond Neptune might preserve the most useful evidence of all. But there is another part of the problem we have avoided so far. We have spent a great deal of time allowing this possible companion to influence comets, capture objects, disturb distant orbits, and generally make itself useful. Eventually we have to get rid of it. Today, there is no star orbiting the Sun at 1,000 astronomical units. There is no hidden second sun somewhere outside the Kuiper Belt. A stellar companion would be very easy to notice. So if the binary hypothesis is correct, the partnership had to end. The timing matters because the star needs to remain long enough to produce the effects we have been discussing, while leaving early enough that the solar system can spend most of its history in the single star configuration we observe today. Its departure also has to happen naturally. We do not want to invent a companion and then require an even more improbable event to remove it. Fortunately, the The Sun's crowded birth environment gives gravity plenty of ways to separate a wide pair. A passing star can exchange energy with the binary. Repeated encounters can gradually weaken the bond. The changing cluster can alter stellar trajectories. If the companion existed, losing it would not require anything especially exotic. In fact, a wide binary inside a crowded young star cluster is exactly the sort of system that can be broken apart by ordinary gravity. The important word is wide. Two stars separated by roughly 1,000 or 1,500 astronomical units can certainly remain gravitationally bound. But compared with stars in a close binary, their connection is weak. The farther apart two stars are, the less orbital energy has to be added before they separate permanently. A close binary is difficult to disrupt. A wide binary is much easier. Modern simulations of star clusters show that wide binaries are particularly vulnerable during the early, dense phases of cluster evolution, when encounters between stars are frequent. Recent direct N-body simulations find that wide systems can experience rapid disruption during the first several million years of a cluster's life, followed by slower evolution as the cluster expands and becomes less crowded. That gives our possible solar twin a very reasonable way out. The Sun and its companion do not need to collide. The companion does not need to explode. The Sun does not somehow push it away by itself. Another star simply has to pass close enough, at the right speed and from the right direction, to change the binary's energy. This is one of those situations where a small change can have an enormous long-term effect. Imagine the Sun and its companion moving around their common centre of mass. For a pair separated by roughly 1,500 astronomical units, one complete orbit would take tens of thousands of years. That sounds slow, and it is. But the system might remain inside the birth cluster for tens of millions of years, so the two stars could still complete many orbits around one another before anything finally separated them. During all of those orbits, neighbouring stars are moving through the cluster. Most pass too far away to matter very much. A few pass closer. Every encounter changes the motion of the binary by some amount. Often the change is tiny. One star might slightly increase the eccentricity of the companion's orbit. Another might change its orientation. A different encounter might make the orbit somewhat wider. The binary survives, but its original configuration gradually becomes less recognizable. Then one particularly important encounter occurs. A third star approaches. As it passes, its gravity pulls differently on the Sun and its companion. Because the stars are separated by a large distance, the passing star does not tug on both members equally. The companion may receive a slightly larger gravitational impulse than the Sun, or the Sun may receive the larger one. What matters is the change in their relative motion. If enough orbital energy is added, the companion's orbit stops being closed. Instead of following an ellipse around the shared centre of mass, it moves onto an escape trajectory. The binary has been disrupted. The companion is now a free star. The 2020 early solar binary model considered exactly this kind of outcome. In that scenario, a roughly solar mass companion separated by around 1,500 astronomical units could plausibly be removed while the Sun was still inside its birth cluster. The authors estimated that disruption in the birth cluster environment was substantially more likely than disruption later in the quieter galactic field. There would probably be no dramatic instant when the separation became visually obvious. At first, the two stars would still be close. Even after becoming gravitationally unbound, the former companion could remain within thousands of astronomical units for quite some time. It is simply no longer following an orbit that will bring it back. The distance begins increasing. 10,000 astronomical units, 20,000, 50,000. Eventually the separation reaches a light year, then several light years. By that stage, the Sun and its former twin look less like a binary and more like two ordinary members of the same stellar group. And even that relationship does not last visually for long. the cluster itself is changing. Young star clusters are not necessarily permanent structures. Some remain gravitationally bound for very long periods, but many associations gradually disperse. Gas left over from star formation can be expelled by radiation and stellar winds. Massive stars evolve rapidly. Some eventually explode. The gravitational potential of the cluster changes. Stars exchange energy through repeated encounters. Some move outward, others escape. The once crowded stellar nursery becomes steadily less crowded. Simulations specifically constructed to follow possible solar birth clusters show that the Sun's original stellar siblings could become widely dispersed through the Milky Way after the cluster dissolves. Their present-day positions depend strongly on the cluster's initial structure and on the gravitational environment through which they subsequently travelled, so our missing companion would not have needed to travel alone immediately. For some period after the binary broke apart, both stars might still have remained members of the same dissolving cluster. They could have continued moving through broadly similar regions of the galaxy. The crucial difference is that they were no longer tied to one another. Their velocities would differ slightly. A very small difference is enough. Suppose two stars separate with only a modest difference in velocity. After 1 year, the distance added by that difference may seem insignificant on a galactic scale. After 1 million years, it is much larger. After 1 billion years, the two stars can be separated by enormous distances, even if their initial departure was rather gentle. You do not need to fire the companion across the Milky Way like a cannonball. You only need to stop it from orbiting the Sun. Time handles the rest. This is especially important because stars do not move through empty, perfectly smooth space. The Milky Way has structure. There is the galactic disk. There are spiral arms. There is a central bar. There are giant molecular clouds containing enormous amounts of gas. There are star clusters and individual stars. Each contributes gravity. Over billions of years, repeated small perturbations alter stellar orbits. A star that once travelled on an orbit extremely similar to the Sun's can gradually become much harder to associate with it. Research combining N-body models of the Sun's birth cluster with galactic structures such as the bar, spiral arms, and giant molecular clouds has shown that solar siblings can be spread over a broad range of galactic orbits. Giant molecular clouds are especially effective at changing stellar motions, increasing the range of places where members of the Sun's original family might be found today. This is where finding the former companion becomes unpleasantly difficult. You might imagine that astronomers could simply measure the motion of every nearby star, run those trajectories backward for 4.6 billion years, and see which one meets the Sun. In principle, that sounds reasonable. In practice, it is not. The first problem is measurement uncertainty. Gaia has transformed astronomy by measuring the positions, distances, and motions of enormous numbers of stars with extraordinary precision. But extraordinary precision is not infinite precision. A tiny uncertainty in a star's present velocity produces a larger uncertainty in its reconstructed position as you calculate farther into the past. After millions of years, that uncertainty grows. After billions of years, simply rewinding a straight-line trajectory is nowhere near enough. The second problem is the galaxy itself. To reconstruct a star's orbit accurately, you need to know the gravitational potential through which it travelled. But the Milky Way today is not an exact map of the Milky Way 4.6 billion years ago. Spiral structure evolves. Molecular clouds form and disappear. Stars migrate through the disk. The galactic bar changes. Individual close encounters are generally impossible to reconstruct once the participants have dispersed. A former companion might have experienced a close encounter with a giant molecular cloud 2 billion years ago that changed its orbit slightly. The Sun might not have experienced the same encounter. Unless we know that ancient clouds' exact mass, location, and motion, the two reconstructed paths will begin drifting apart from the true history. The farther backward we go, the worse the problem becomes. It is like trying to reconstruct the precise path of two leaves floating down a river several hours after they disappeared around a bend. Knowing the current shape of the river helps. Knowing exactly how every current and gust of wind behaved would help more. Astronomy does not have security footage. There is another complication. The companion may not have left in a simple two-star interaction. Star clusters contain binaries, triples, and larger multiple systems. A passing object might itself have been a binary. Encounters involving several stars can exchange members and rearrange systems in complicated ways. A star that begins as one member of a binary can end an encounter single. A single star can replace one member of a binary. A binary can become tighter, while another star is ejected. Strong stellar encounters in clusters are capable of changing binary orbital parameters and exchanging stars between systems. In sufficiently busy environments, some encounters can even be interrupted by additional stars arriving before the first interaction is finished. So even the phrase, "the star that ejected the Sun's twin," might be too simple. There may have been one important passerby. There may have been several weaker encounters. The companion's orbit may have widened gradually before one final disturbance unbound it, or a more complicated interaction could have changed several stellar trajectories at once. From our point of view today, all of those possibilities end the same way. One star remains as the centre of our solar system. The other leaves. The breakup could also have affected the distant objects we discussed earlier. If a passing star came close enough to disrupt a wide solar binary, it would also exert gravity on the outer Oort Cloud. That is an important detail because the companion cannot be removed independently of everything around it. The same encounter capable of separating two stars can perturb loosely bound comets. In the Sirajan Loeb model, the closest stellar encounter responsible for unbinding the solar companion could remove a large fraction of the distant bodies captured during the binary phase, while still leaving enough survivors to produce the desired outer Oort Cloud population. Their calculation therefore treats the breakup not merely as a way to remove the twin, but as part of the final filtering of the captured population. That gives the possible separation a rather unusual role. First, the companion helps capture objects. Then, the encounter that removes the companion removes many of those objects. The survivors become the interesting population. It sounds inefficient. Nature is often inefficient. Stars form from clouds while much of the original gas is expelled. Planets form from disks while enormous amounts of material are lost. Planetary systems eject planetesimals by the billions. Evolution does not generally seem concerned about keeping the workspace tidy. The binary model only needs the surviving fraction to resemble the population we infer today. And once the companion is gone, those survivors find themselves orbiting a different system. Before the breakup, their motion was influenced by two stars. Afterward, the Sun becomes the only nearby stellar mass. Some objects remain securely bound, some leave. Some may follow the companion. Others enter new orbits around the Sun. The exact outcome depends on where each object happened to be when the disruptive encounter occurred. That would make the final separation an important event in the construction of the outer solar system. Closer to the Sun, the planets barely notice. At thousands or tens of thousands of astronomical units, the consequences can be substantial. The difference again comes down to binding energy. Earth is held tightly by the Sun. A comet 40,000 astronomical units away is not. Removing a solar mass companion and simultaneously allowing another star to pass nearby is a much larger event from the comet's point of view. This is one reason the Oort Cloud can preserve information about the Sun's early stellar environment, while Earth does not. The ancient stellar neighbourhood had more leverage at large distances. After the birth cluster finally dissolved, the Sun entered something closer to its present lifestyle. It continued orbiting the centre of the Milky Way. Its former neighbours spread through the disk. Close stellar encounters became less frequent. The major planets continued evolving, but the era of frequent cluster interactions ended. The Sun was now, for practical purposes, a single field star. And somewhere else, if our hypothetical companion survived the encounter normally, another field star continued its own life. That companion would probably not know anything had happened, in the sense that stars know nothing at all. It would simply continue converting hydrogen into helium if it were a normal main sequence star. If its mass were close to the Sun's, it could still be shining today. A Sun-like star can remain on the main sequence for around 10 billion years, so a companion born 4.6 billion years ago would not automatically have evolved into a stellar remnant by now. If it were somewhat less massive than the Sun, its main sequence lifetime would be even longer. That gives us a strange but perfectly ordinary possibility. The missing star may still exist. It could be in a constellation visible from Earth. It could be too faint to see without a telescope. It could be on the other side of the galactic disk. We do not know. And there is no requirement that it still resemble the Sun perfectly. Stars of the same age can evolve at different rates if their masses differ. A companion slightly more massive than the Sun would have progressed farther through its stellar life. A significantly more massive one might already have evolved away from the main sequence. A lower mass companion could look much redder and dimmer. The convenient picture of two identical yellow suns is only one version of the idea. The binary model that motivated much of our discussion used an approximately equal mass companion because that configuration provides strong capture efficiency and can remain compatible with the proposed distant populations. But an actual stellar companion, if one existed, would have had its own exact mass, chemical composition, rotation, magnetic history, and perhaps its own planets. That last possibility is worth considering. If the twin possessed a protoplanetary disk, it could have formed a planetary system before the binary was disrupted. When the two stars separated, those planets would remain with whichever star held them most tightly. So somewhere in the Milky Way, there could theoretically be a planetary system that formed beside ours. Its star would have shared part of the Sun's early environment. Its planets would have formed at roughly the same period as Earth and Jupiter. Its distant comets might even contain material exchanged with the early solar system. There is no evidence that such a system exists, but nothing about the basic dynamics makes the possibility absurd. And if the companion remained intact after leaving, it would spend the next billions of years experiencing its own galactic history. Perhaps it passed near other stars. Perhaps its planets were disturbed. Perhaps it migrated to a different part of the galactic disk. Maybe it stayed relatively close to the Sun for a long period, before gradually drifting away. Maybe their galactic orbits separated rapidly. The answer depends on the exact velocity the star received when the binary broke apart. A tiny difference at the beginning can produce a huge separation after 4.5 billion years. That is why present distance alone tells us almost nothing. The nearest Sun-like star today is not automatically a good candidate. A very distant star is not automatically impossible. Astronomers instead need several clues at once: age, chemistry, motion, position, stellar mass, detailed elemental abundances, and ideally, a galactic orbit that can be made consistent with a shared origin once uncertainties are considered. This is already the method used in searches for ordinary solar siblings. Those searches do not specifically assume the candidate was once bound to the Sun. They simply try to identify stars that may have formed in the same birth cluster. Researchers using apogee chemistry together with Gaia motions have identified candidate stars whose properties are compatible with a common birth environment. But simulations also show that distinguishing genuine siblings from unrelated stars is difficult after billions of years of galactic mixing. A former binary companion would be an even more demanding identification. Imagine finding a star with exactly the Sun's age. Interesting, but millions of stars in the galaxy are approximately the same age. Now suppose its ion abundance matches the Sun's. Better. Still not enough. Add magnesium, silicon, calcium, nickel, carbon, oxygen, and many other elements. If the detailed chemical pattern becomes extremely similar, the candidate becomes much more interesting. Stars forming from the same well-mixed cloud can preserve similar chemical abundance patterns, which is why chemical tagging has become an important part of the search for dispersed stellar families. But chemistry alone cannot prove a binary relationship. Two unrelated stars can resemble each other chemically, and the material within a star-forming region may not have been perfectly uniform. Then there is motion. Perhaps the candidate's velocity through the galaxy is broadly similar to the Sun's. That helps. But after 4.6 billion years, a genuine sibling does not necessarily need to have nearly identical motion today. Simulations show that spiral arms, the galactic bar, and giant molecular clouds can substantially redistribute stars that began together. This means the perfect candidate may not look obvious at all. It might be hidden among ordinary stars. Its spectrum may reveal a suspicious chemical resemblance. Its age may match. Its galactic orbit may be broadly compatible. But proving that it once sat 1,000 astronomical units from the young Sun is another level of difficulty entirely. There may be no surviving measurement capable of establishing that relationship beyond reasonable doubt. The best evidence might instead remain here, not in the star, in our own outer solar system, a population of captured dwarf planets, an unusual structure in the Oort Cloud, a distant planet with properties suggesting capture, orbital distributions that repeatedly favour models containing an early companion. If several independent clues eventually point toward the same binary history, then astronomers could begin taking individual stellar candidates more seriously. The problem can therefore be approached from both directions. Start with the solar system and reconstruct the kind of companion required. Start with the Milky Way and search for stars that could fit that history. Eventually, perhaps, the two searches meet. At present, they do not. The Sun remains single. Its birth cluster has dispersed. No confirmed stellar twin has been identified. The early binary scenario remains a hypothesis rather than a recovered piece of solar family history. The original proposal itself presents the companion as a temporary model intended to explain properties of the distant solar system, not as a discovered star. But the absence of a known companion is exactly what the model expects. The star is supposed to be gone. The question is whether gone means completely unrecoverable. Gaia has given astronomers positions and motions of stars with a precision that would have been unimaginable only a few decades ago. Large spectroscopic surveys can measure chemical fingerprints for enormous stellar samples. Computers can simulate dissolving clusters inside evolving models of the Milky Way. Those tools allow astronomers to search for the Sun's lost family on a scale that was previously impossible, and somewhere inside those catalogues there may be stars that formed close to ours. One of them perhaps came much closer than all the others. If the Sun truly began life as half of a binary, identifying that one star would require much more than finding something that looks vaguely solar. That is where the search becomes less about how the twin disappeared, and more about whether we could ever know it again if we happened to find it. Finding such a star would be one of those scientific problems that sounds much easier when reduced to a single sentence. Find a star that used to orbit the Sun. There we are. Someone start looking. The difficulty becomes apparent almost immediately. Because the Milky Way contains hundreds of billions of stars, the possible separation happened roughly 4.6 billion years ago, and our hypothetical companion has had almost the entire age of the solar system to disappear into the galactic population. It would not necessarily look unusual today. It would not be moving through space with a small sign attached to it saying, "Formerly associated with your Sun." If its mass were close to the Sun's, it could simply look like another ordinary middle-aged star, and there are plenty of those, so astronomers would need to identify it indirectly, using several different kinds of evidence. The first would be age. Any genuine companion born alongside the Sun should be approximately as old as the Sun itself, around 4.6 billion years. That immediately removes many stars from consideration. A star only 1 billion years old cannot have formed beside the Sun. A star 10 billion years old cannot have done so either. But age is not nearly precise enough to solve the problem by itself. The Milky Way formed stars continuously over billions of years. There are enormous numbers of stars with ages broadly compatible with the Sun's. and measuring the age of an ordinary main sequence star is surprisingly difficult. Stars do not come with annual rings. For clusters, astronomers can compare many stars at different evolutionary stages and estimate a shared age. For an isolated Sun-like star, the uncertainties can be considerably larger. Researchers can compare a star's temperature, luminosity, metallicity, and other properties with theoretical stellar evolution models. In some cases, rotation or astroseismology can add useful information. But determining that a star is approximately 4.6 billion years old is very different from proving that it formed on the same day, in the same cloud, and beside the same protostar as our Sun. Age is therefore a filter, a useful one, but nowhere near a fingerprint. The next clue would be chemistry. This is where things become much more interesting. Stars preserve information about the material from which they formed. Most of a star is hydrogen and helium, but the small fraction made of heavier elements can be measured through spectroscopy. When astronomers spread starlight into a spectrum, different elements leave characteristic absorption lines. Iron leaves one set, magnesium another. Silicon, calcium, nickel, titanium, carbon, oxygen, and many other elements contribute their own features. By measuring those lines carefully, astronomers can build a detailed chemical profile of a star. The idea behind chemical tagging is that stars born from the same well-mixed cloud should begin with very similar elemental abundance patterns. So if we are searching for the Sun's original family, we can look for stars whose chemistry resembles the Sun's in unusually fine detail. This technique has already been used in searches for ordinary solar siblings. One study examined 30 candidate stars in detail and found that only 2 showed strongly solar chemical compositions. Of those, HD 162826 also satisfied the author's dynamical criteria and was proposed as a particularly strong candidate for having formed in the Sun's birth cluster. That did not establish it as a former binary companion, and later work has continued to treat solar sibling identification as a difficult candidate selection problem rather than a solved family reunion. Another search using the AMBRE spectroscopic database began with roughly 17,000 stars, narrowed the sample using metallicity and detailed abundances, then considered stellar ages and Gaia motions. 4 especially promising candidates remained, with HD 186302 described as the most precisely characterized candidate in that analysis. The researchers also suggested that isotopic ratios and better age measurements could help distinguish genuine siblings from stars that merely look chemically similar. Notice what is happening here. 17,000 stars become 55, 55 become 12, 12 become 4. And even then, nobody opens a bottle of champagne and announces that the Sun's family has been found. Astronomy can be impressively cautious when required. Chemical similarity is powerful, but it has limits. Different clouds within the Milky Way can produce stars with broadly similar compositions. 2 unrelated stars may both have nearly solar metallicity. Even several matching elemental abundances may not be enough. The goal is therefore to measure many useful elements with very high precision, particularly elements whose abundances vary significantly between unrelated stars. Rare elements and neutron capture elements can be especially valuable because they add additional dimensions to the chemical comparison. Isotopic ratios could provide still more information. The more detailed the chemical pattern, the less likely a close match becomes by coincidence. But even a perfect chemical match would establish, at best, a strong shared origin candidate. It would not automatically prove that the star was the Sun's companion. Remember the difference we made earlier. A solar sibling is any star that formed in the same stellar nursery. If the Sun's birth cluster contained hundreds or thousands of stars, there could have been many solar siblings. The lost twin, if it existed, would be one particular sibling that became gravitationally bound to the Sun. Finding someone who attended the same school is not the same as finding the person who shared your desk, so chemistry has to be combined with motion. This is where Gaia changed the search dramatically. ESA's Gaia mission measured stellar positions, parallaxes and proper motions on an enormous scale. Gaia Data Release 3 includes astrometric solutions for about 1.46 billion sources, giving astronomers precise measurements of where stars are, how far away many of them are, and how they move across the sky. Radial velocities for many stars add motion toward or away from us, allowing researchers to reconstruct three-dimensional stellar velocities. Before Gaia, searching for the Sun's dispersed family was rather like trying to identify former classmates using blurry photographs and approximate addresses. Gaia improved the addresses considerably. A candidate's sibling can now be checked against several quantities at once. Where is it? How fast is it moving across the sky? How fast is it moving toward or away from us? What orbit does that imply around the Milky Way? Does its motion make any sense for a star that might once have occupied the Sun's birth cluster? For relatively recent stellar encounters, orbital reconstruction can work remarkably well. Gaia proper motions are precise enough to follow the expected motion of nearby stars over hundreds of thousands of years, and ESA has demonstrated trajectories for tens of thousands of nearby stars over such timescales. But our problem is not hundreds of thousands of years, it is billions. That is a very different challenge. Suppose we know a candidate star's velocity with extraordinary precision. Even a tiny uncertainty becomes important when multiplied by 4.6 billion years. And the star has not spent all that time moving in a straight line. It has been orbiting the Milky Way. So has the Sun. Both have felt the gravitational influence of the galactic disk. Both have responded to the central concentration of mass. Their paths may have been affected by spiral structure. They may have passed giant molecular clouds. They may have experienced distant encounters with other stars. The Milky Way itself has evolved during that time. This makes simply pressing a theoretical rewind button extremely unreliable. Models of the Sun's birth cluster show exactly this problem. When researchers include the galactic bar, spiral arms, and giant molecular clouds, stars that began together can become widely dispersed, and their present-day phase space distribution changes substantially depending on the galactic model used. In particular, giant molecular clouds can scatter cluster members enough to complicate efforts to reconstruct their original association billions of years later. That means a genuine solar sibling might have a present-day orbit that does not look especially similar to the Sun's. Conversely, an unrelated star might happen to occupy an orbit that looks promising. Motion helps. It does not settle the case. The former companion would be harder still. If the binary was disrupted by a stellar encounter, the companion would leave with some relative velocity compared with the Sun. We do not know what that velocity was. We do not know the direction. We do not know exactly when the disruption happened. We do not know which star caused it. And if several encounters gradually widen the binary before the final escape, reconstructing one neat departure trajectory may not even describe the real event very well. There is another subtle problem. The stars we search today are not necessarily still near us. Early searches often concentrated on the solar neighbourhood, because those stars are easier to observe in detail. That makes practical sense. But a star born beside the Sun does not have to remain beside the Sun. After billions of years of galactic mixing, solar siblings can occupy a much larger region of the galactic disk. Numerical studies of dissolving solar birth clusters have shown that the original stellar family can spread widely, meaning that searching only the immediate neighbourhood may miss most of it. Our lost twin could therefore be far away, perhaps hundreds of light years, perhaps thousands, possibly much farther, depending on its escape velocity and subsequent galactic history. Distance introduces another observational problem. A nearby Sun-like star can be studied with extremely high-resolution spectroscopy. A faint star on the far side of the galactic disk is much more difficult. Its chemistry becomes harder to measure precisely. Its age may be less certain. Dust can obscure it. Crowded stellar fields make observations more complicated. There could be an excellent candidate sitting in a catalogue while nobody realises that it deserves special attention. This is why large surveys matter. Gaia provides astrometry. Ground-based spectroscopic programs add chemical abundances and radial velocities. Researchers can then combine those datasets and search enormous stellar samples for objects satisfying several requirements at once: correct age, solar-like detailed chemistry, compatible motion, plausible galactic orbit, perhaps unusual isotopic similarities. Each criterion removes more unrelated stars. Eventually you hope that only a manageable number of candidates remain. Then astronomers can observe those candidates much more carefully. It is a little like searching an enormous pile of keys. First remove every key that is obviously the wrong size, then remove the wrong shape, then the wrong material. Eventually you're left with 3 keys. Unfortunately, the lock disappeared 4.6 billion years ago. That last part is the difficulty. Even if astronomers found an extraordinary solar sibling tomorrow, how would they prove it was specifically the companion? Suppose we find a star with an age matching the Sun. Its metallicity is almost identical. 20 or 30 elemental abundance ratios agree beautifully. Its isotopic composition looks remarkably similar. Its current motion is compatible with models of the dispersed solar birth cluster. Every available test says this star probably formed alongside the Sun. That would be a major discovery, but it would still establish only a sibling. To identify the former binary partner, we would need some additional connection. Perhaps detailed dynamical modelling could show that, across a range of plausible galactic histories, this candidate repeatedly emerges as unusually likely to have occupied the correct region near the Sun early on. That would help. But after 4.6 billion years, obtaining the precision needed to demonstrate a separation of only 1,000 astronomical units at birth would be extraordinarily difficult. 1,000 astronomical units sounds enormous inside the solar system. On galactic scales, it is almost nothing. For comparison, 1 light-year is about 63,000 astronomical units. So distinguishing 2 stars that were 1,000 astronomical units apart from 2 stars that were 100,000 astronomical units apart nearly 5 billion years ago requires reconstructing their ancient positions with remarkable accuracy. Our uncertainty would almost certainly be much larger than the binary separation itself. This is why the strongest evidence for the twin may never come from rewinding the twin's orbit. It may come from combining stellar evidence with the solar system evidence we have been discussing all along. Suppose future surveys reveal a large population of distant dwarf planets whose orbital distribution closely matches the predictions of an early solar binary. Suppose improved models show that the outer Oort Cloud is difficult to reproduce without the enhanced capture efficiency of a temporary companion. Suppose astronomers then identify one chemically exceptional solar sibling with the correct age and a plausible galactic history. None of those clues alone would prove anything. Together they would be much more interesting. Then imagine that this candidate star has its own planetary system. That could provide another set of clues. If the 2 stars formed together, their planets would have developed in the same broad cluster environment. There is no reason the planetary systems would need to look alike. Protoplanetary disks vary enormously, and planet formation is chaotic. But detailed chemical comparisons might become possible. Perhaps primitive material around both stars preserves related isotopic signatures. Perhaps unusual abundance patterns associated with planet formation could be compared. This is highly speculative, because we do not currently possess anything close to the measurements needed to identify a former companion this way. Still, it shows how an eventual case might be built. Not one clue, many. Astronomers already know that chemical tagging benefits from combining abundance information with age and kinematics, rather than relying on chemistry alone. Searches for solar siblings have repeatedly narrowed large samples to small sets of candidates, but have not produced an uncontested identification of the Sun's original stellar family. The next improvement comes from better data. Gaia itself completed its science observations on January 15, 2025, and the spacecraft was passivated on March 27th of that year but the scientific processing continues. ESA's current release information lists Gaia Data Release 4 as an upcoming release based on 66 months of observations, with a much larger set of products than DR3, while the final Gaia catalogue is planned from the full mission dataset. Better stellar motions and additional astrophysical information will give future solar sibling searches a stronger starting point. More precise astrometry helps narrow candidate motions. Better spectroscopy improves chemical tagging. Astroseismology can improve ages for suitable stars. Larger samples increase the chance that a genuine sibling is included at all. And better models of galactic evolution help astronomers understand how widely the Sun's birth family should have dispersed. Yet there may always be a limit. Some information is genuinely lost. If two stars separated billions of years ago and then experienced independent gravitational perturbations, their exact ancient trajectories may no longer be reconstructible from present measurements. This does not mean the past ceased to happen. It means the surviving evidence may not uniquely determine it. Science encounters this problem frequently. We know a glass broke because the pieces are on the floor. We may be able to determine where it stood and approximately how it fell. Determining the exact position of every fragment 1 millisecond before impact is another matter. The Sun's binary childhood may be similar. We may eventually become confident that a companion probably existed without ever identifying the individual star. Or we may identify several plausible solar siblings but remain unable to determine whether any one of them was gravitationally bound to the Sun. There is also the possibility that the companion no longer exists in an easily recognizable form. If it was more massive than the Sun, its stellar evolution would have proceeded faster. Depending on its original mass, it might now be a white dwarf or, if it was much more massive, have undergone an even more dramatic evolution. The equal mass companion usually considered in the temporary binary hypothesis would still be expected to resemble an ordinary middle-aged star, but the hypothesis itself does not give us a known spectral type, catalogue number, or present location. The companion remains a proposed dynamical ingredient, not a detected object. There is something useful about keeping that distinction clear. The Sun definitely formed. The solar system definitely contains strange, distant objects. Stars definitely form in multiple systems. Wide binaries definitely can be disrupted. The Sun probably formed in a populated stellar environment. Solar siblings should have existed. Astronomers can search for them. But the specific statement that the Sun had a wide companion that helped populate the Oort Cloud remains a hypothesis. An interesting one, a testable one, but still a hypothesis. And that means the search has two possible outcomes that are equally valuable. Perhaps future observations will make the binary model unnecessary. A better understanding of Neptune's migration, stellar flybys, galactic tides, and the Sun's birth cluster might explain the distant solar system without requiring a bound companion. If so, the missing twin may turn out never to have existed. Or perhaps the opposite happens. New distant objects are discovered. Their orbits fit the binary predictions. The inferred Oort Cloud population becomes easier to reproduce with two early stars than one. Chemical surveys identify an unusually convincing solar sibling. Improved galactic models show that its motion is compatible with the Sun's birth environment. The evidence begins pointing repeatedly toward the same early history. In that case, the solitary Sun we see every day would acquire a rather different biography. For the first part of its life, it may have been one member of a pair. The planets would have formed beneath the combined gravitational influence of a binary system, although the second star remained far away. Comets and distant planetesimals would have moved through a more complicated outer environment. Some objects might have been captured, others might have been lost. Then the birth cluster dispersed, the stellar partnership broke apart, and the Sun continued alone with the planets and distant debris that remained. The companion continued somewhere else. 4.5 billion years later, one of those planets developed telescopes capable of measuring the motion and chemistry of stars across the galaxy. And now we're using them to ask whether the star beside our Sun at the beginning might still be out there. We may never find it. We may eventually find a star that looks almost suspiciously right, or the real breakthrough may come from the objects much closer to home, where ancient gravitational disturbances remain recorded in distant orbits. Either way, the question changes something about how we look at the Sun. It seems isolated because that is how we encounter it now. One star, 8 planets, a large population of smaller bodies. But the solar system we see today is the result of a long history in which objects formed, migrated, collided, escaped, and disappeared. A former companion would simply be the largest missing object in that history. So the next time you see sunlight coming through a window, it may be worth remembering that the star producing it has been travelling through the Milky Way for about 4.6 billion years. For most of that journey, as far as we can tell, it has travelled without a stellar companion. Whether it began that way is still uncertain. Somewhere among the billions of stars measured by our surveys may be members of the Sun's original family. Perhaps one of them once orbited far closer to the Sun than Alpha Centauri does today. Perhaps it carried away its own planets and comets when the pair separated. Perhaps it is still quietly shining somewhere in the galactic disk, completely indistinguishable to the eye from thousands of other points of light, and perhaps we will never know which one it was. For now, that uncertainty is part of the science. We can measure the surviving clues, we can test the orbital predictions, we can compare the chemistry of stars, we can improve the models, and slowly, candidate by candidate, and distant object by distant object, we can narrow the range of possible beginnings for our solar system. This Sun may always turn out to have been born alone, but it may also have spent its earliest years with another star close enough to change what survived at the edge of the solar system, before gravity separated them and the Milky Way carried them in different directions. If that star is still out there, then somewhere in the sky is an object that once shared the Sun's first home. We just don't know which point of light it is yet,